Hello and welcome to Space Historians. I am truly glad you have joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our little blue world. Tonight, we are not racing through the stars, we are gliding gently, letting the silence of space wrap around us like a soft blanket. This is your moment to leave behind the noise of the day and step quietly into the vast, starlit corridors of cosmic history. Before we begin, I would love to know, where in the world are you listening from, and what time is it where you are? It always amazes me how, while the night sky may look different across the globe, the stars above have watched over every civilization in history. If you enjoy these quiet journeys through time and space, a like and a subscribe help keep this channel orbiting steadily. And for those who have already joined this growing constellation of listeners, thank you. You are part of this voyage, part of this shared wonder. Each episode here is not just about stars, planets, or galaxies. It is about the stories they hold, the myths whispered by ancient astronomers, the discoveries that changed how we see the universe, and the quiet mysteries still waiting to be revealed. So tonight, as your eyes grow heavy and your breathing slows, imagine yourself floating slowly past the edge of Earth's atmosphere. The air grows thin, the blue fades to black, and there, a vast canvas of history and starlight stretches out before you. Every shimmering star is a chapter. Every faint glow is a story. If you gently press the notification bell, you will always know when the next journey begins. But for now, you do not need to do anything but listen, breathe, and drift. Tonight, we are going to explore something extraordinary. A question that sounds simple but opens doors to immensity. How big is the Andromeda galaxy really? Not just in numbers, though we will share those, but in meaning, in perspective, in the quiet wonder of knowing that when you look up on a clear night, you can see with your own eyes another galaxy, another island universe, containing nearly 1 trillion suns. Let us travel together, back through the ages of discovery, into the depths of cosmic measurement, and forward toward a future when these two great galaxies will dance together. Welcome to the quiet side of the cosmos. There is something hanging in your night sky that should not be possible to see. It is so far away that its light has been travelling toward you for 2.5 million years. It began its journey before your species learned to speak, before anyone built the first shelter, before humanity had any concept of what a star might be. And yet, if you know where to look on a clear autumn evening, you can see it with nothing more than your eyes. No telescope. No instruments. Just you, standing beneath the darkness, letting your vision adjust, and there it is. A faint smudge of light. Modest, almost shy. Easy to miss if you do not know it is there. That smudge is the Andromeda galaxy, another entire galaxy, separate from our own, containing close to 1 trillion stars. Think about that for a moment. 1 trillion. If you tried to count them, one star every second without stopping, you would need more than 30,000 years to finish. And every single one of those stars is gathered into a structure so vast that if you could somehow travel at the speed of light, the fastest speed in all of existence, it would still take you 220,000 years to cross from one side to the other. All of that, visible to your naked eyes. All of that light, compressed into a blur no brighter than the faintest stars around it. It is one of the most astonishing facts in all of astronomy, and it happens every clear night, whether anyone notices or not. The photons streaming into your eyes right now left Andromeda when early humans were still learning to shape tools from stone. While those ancient people looked up at the same sky, the light that would eventually reach your eyes tonight was already halfway through its journey across the void. The galaxy you see is not Andromeda as it exists now, but as it was in the deep past, a living fossil suspended in transit. And here is what makes it even more extraordinary. You are not seeing all of it. What your eyes can gather is only the brightest core. The dense central bulge where stars crowd together. The full extent of the galaxy, if your vision were sensitive enough, would span an area of sky several times larger than the full moon. Imagine that. A galaxy, hanging above you, wider than the moon, filled with structure and light, invisible only because our eyes are too weak to collect it all. But it is there, always there, patient, waiting. When ancient Persian astronomers noticed this blur over 1,000 years ago, they called it the Little Cloud. They had no idea what it truly was. To them, it was a mystery. Something that did not fit the patterns of stars or planets, something faint and fuzzy that refused to sharpen into clarity. For centuries, it remained in that category. A curiosity, a footnote in star catalogues. It was not until the 1920s that humanity finally understood. Edwin Hubble, using the most powerful telescope of his time, identified individual stars within that blur and measured their distance. The numbers were staggering. Andromeda was not a cloud of gas within our galaxy. It was an entirely separate galaxy, far beyond anything we had imagined. With that single discovery, the universe expanded overnight. The Milky Way was no longer the whole cosmos. It was just one island among countless others, and Andromeda was our nearest neighbour. That moment reshaped everything. It told us that the universe was not small or contained. It was vast, almost beyond comprehension, filled with galaxies stretching in every direction, each one a system of billions or trillions of stars. And the proof had been hanging in our sky all along, visible to anyone who looked up. Even now, knowing what we know, it still feels impossible. How can something so immense appear so faint? How can 1 trillion stars compress into a blur smaller than a coin held at arm's length? The answer lies in distance, in the sheer gulf of space that separates us, but also in the nature of light itself. Every photon is a messenger, carrying its signal across millions of years, and by the time it arrives, it has spread so thin that only the faintest whisper remains. And yet that whisper is enough. Enough to see, enough to measure, enough to understand that we are not alone in the universe, that our galaxy is part of a family, and that Andromeda, the largest member of that family, is both impossibly distant and strangely close. Tonight, as you settle into stillness, imagine standing outside under a sky dark enough to see it. The air is cool, the stars are sharp. You let your eyes adjust, and slowly, you notice that faint, oval glow. You know what it is now. You know that within it are worlds beyond counting, stars in their billions, perhaps even civilizations looking back at us from across the void. You know that it is moving toward us, that in billions of years our galaxies will merge, reshaping the sky in ways we can only imagine. But for now, it is simply there, a soft light, a reminder, a question written across the heavens. How big is Andromeda really? That is what we are here to explore, not just in numbers, though we will share those, but in meaning, in perspective, in the quiet recognition that the universe holds scales so vast that our minds can barely grasp them, and yet we try, we reach, we wonder. This is where the journey begins, with that impossible blur, with your eyes, unaided and ancient, seeing across 2.5 million years of space, with the knowledge that size is not just about measurement, but about understanding what it means to exist in a universe where galaxies are neighbours, where light carries history, and where a faint smudge in the sky can hold 1 trillion suns. Let that thought settle as your breathing slows. Let the immensity wash over you gently. There is no rush. We have all night to drift through the story of Andromeda, to trace its size through history, through science, through the eyes of those who wondered before us. The impossible is possible. You can see another galaxy, and from that simple fact, everything else unfolds. Long before anyone understood what a galaxy was, before the word even existed in the way we use it now, people noticed the faint blur in the constellation of Andromeda. They did not know what they were seeing, but they saw it nonetheless. And that act of noticing connects us across thousands of years to observers who stood beneath the same sky. The earliest written record we have comes from the year 964, from a Persian astronomer named Abd al-Rahman al-Sufi. He was compiling what would become one of the most important astronomical texts of the medieval Islamic world, a book called the Book of Fixed Stars. In it, he catalogued the stars visible to the naked eye, their positions, their brightness, the patterns they formed. And among those entries, he described something unusual. He called it the Little Cloud. It sat in the constellation of Andromeda, that figure from Greek mythology. The princess chained to a rock as punishment for her mother's pride, later rescued by the hero Perseus. The constellation itself was well known, its bright stars easy to find, arcing across the autumn sky. But nestled within it was this faint, diffuse patch, something that did not behave like a star. It did not twinkle. It did not have sharp edges. It was simply there, soft and persistent, refusing to be anything other than itself. Al-Sufi noted its position carefully, describing where to find it relative to the nearby stars. His record was precise enough that later astronomers could identify exactly what he had seen. And what he had seen, though he could not have known it, was another galaxy, an entire island universe, home to 1 trillion stars, visible as nothing more than a smudge. But Al-Sufi was not the first to see it. He was simply the first we know of to write it down. Before him, countless people must have noticed the blur. Ancient Greek astronomers who mapped the constellations, Babylonian stargazers who tracked the motions of planets, indigenous peoples across the world who used the night sky as a calendar, as navigation, as myth. The little cloud was there for all of them, patient and unchanging, waiting for someone to ask what it was. In those ancient times, the night sky was different from what most of us see today. There were no cities flooding the darkness with electric light, no street lamps, no glowing screens. When the sun set, the stars emerged in their full glory, thick and bright, the Milky Way a river of light cutting across the heavens. Such darkness, even faint objects became visible to careful eyes. Andromeda would have been more accessible then, easier to notice for those who spent their nights watching. And people did watch. Across cultures, across continents, the sky was not just a backdrop but a presence, a constant companion. Farmers read the stars to know when to plant, sailors navigated by them. Storytellers wove them into myths that explained the world. The stars were not distant abstractions. They were part of daily life, familiar and intimate. To those observers, the little cloud was a puzzle. It did not move like a planet, which wanders slowly against the fixed stars. It did not change like a comet, which appears suddenly and fades. It was simply always there, in the same place, faint and fuzzy. Some might have thought it a gathering of stars too faint to see individually. Others might have imagined it as a cloud of luminous gas. Still others might have attached no explanation at all, content to observe, without needing to understand. The Greeks, who gave us the constellation Andromeda, may have known the blur, though we have no surviving text that mentions it explicitly. Their astronomy was sophisticated, their records detailed, but much has been lost to time. What we do know is that they recognized patterns in the sky, grouping stars into figures that told stories, and within those patterns, any faint object would have been noticed, at least by the most attentive observers. By the time Al-Sufi catalogued it, the blur had likely been seen by thousands of people across generations, each noticing it in their own way, each perhaps wondering what it might be. Al-Sufi's contribution was not discovery, but documentation. He wrote it down, he preserved it, and in doing so, he ensured that future astronomers would know where to look. After Al-Sufi, the little cloud appeared in other catalogues. Medieval European astronomers, translating and building on Islamic texts, included it in their own maps of the heavens. It became a known object, familiar to anyone who studied the stars, even if its nature remained mysterious. For centuries, it stayed in that category. A curiosity, something recognized but not explained. What makes this history so striking is how universal the act of noticing was, across cultures that never communicated, across languages and traditions that developed independently. People looked up and saw the same faint blur. Some recorded it, others may have told stories about it. Still others simply filed it away in memory, a small detail in the vast canvas of the night, and all of them, without knowing it, were seeing the same thing. A galaxy. a structure so immense that it defies comprehension, yet so distant that it appears as nothing more than a whisper of light. The little cloud was not little at all. It was vast beyond imagining, but to the naked eye it was humble, almost invisible, easy to overlook. The patience of the sky is remarkable. For thousands of years, Andromeda hung there, unchanged, while civilizations rose and fell beneath it. Empires expanded, languages evolved, technologies advanced, and through it all, the faint blur remained, constant and quiet, offering itself to anyone who cared to look. There is something deeply human in that continuity. The same photons that reached Al-Sufi's eyes in the year 964 are cousins to the photons reaching yours tonight. The light is always arriving, always new, always ancient. Every generation sees the same galaxy, though each sees it through different eyes, different understandings, different questions. For the people who first noticed it, the little cloud was a mystery without answers. They could observe it, map its position, describe its appearance, but they could not explain it. They did not have the tools. They did not have the framework. The concept of a galaxy did not exist yet. The idea that the universe might contain countless islands of stars, each separated by unimaginable distances, had not been imagined. And yet, they looked. They noticed. They recorded. And in doing so, they began the long process of understanding, a process that would take centuries to unfold, that would require the invention of telescopes, the development of new physics, the patient work of countless astronomers building on one another's discoveries. But it all started here, with the act of noticing, with someone standing beneath the night sky, letting their eyes adjust, and seeing that faint blur in the constellation of Andromeda, with someone deciding it was worth writing down, worth preserving, worth passing on to the next generation. That is where it all began. Not with measurement or theory, but with simple observation, with the human capacity to see something small and wonder if it might be something more. The little cloud was patient. It waited. And eventually, humanity would find the tools to see it for what it truly was. But first, there were centuries of watching, centuries of cataloguing, centuries of that faint blur sitting quietly in the sky, holding its secret, waiting for the moment when someone would finally ask the right question and have the means to answer it. For hundreds of years after Al-Sufi first wrote about the little cloud, it remained exactly that. A little cloud, a fuzzy patch, a nebula, which simply meant cloud in Latin. Astronomers knew where to find it. They could point telescopes at it. They could describe its appearance in ever greater detail, but its true nature stayed hidden behind a wall of assumptions about what the universe was. The breakthrough came not suddenly, but gradually, through a series of observations that built upon one another like stones stacking into a cairn. Each stone was small, but together they pointed toward something extraordinary. The first hint arrived in the early 1600s, when telescopes were new, and the act of looking through glass at the heavens was still revolutionary. Simon Marius, a German astronomer, turned his telescope toward the Andromeda constellation in 1612 and observed the nebula carefully. What he saw was different from a star. Instead of a sharp point of light, it appeared as a diffuse glow, larger than any star, with a brighter centre that faded gradually toward the edges. He described it as resembling a candle flame seen through horn, that translucent material people used before glass became common. The comparison was apt. The nebula had a soft quality, a gentle luminosity that did not have hard boundaries. Marius noted that it was visible to the naked eye on dark nights, but through his telescope it became more distinct, more obviously something other than a simple star. Still, even with this closer look, the question remained. What was it? A cloud of glowing gas within the Milky Way? A cluster of stars too faint and distant to be resolved individually? Something else entirely? The tools of the time could not answer. They could only describe. Over the following centuries, better telescopes revealed more detail. William Herschel, who discovered Uranus in 1781, systematically observed nebulae throughout the sky, cataloguing them, describing their shapes. He noticed that some nebulae could be resolved into individual stars with powerful enough instruments, while others, including Andromeda, remained stubbornly fuzzy. He speculated that perhaps with an even more powerful telescope, all nebulae would eventually resolve into stars, suggesting they were distant clusters within our own galaxy. But Andromeda resisted this explanation. Even as telescopes improved, even as astronomers could see farther and clearer, the Andromeda Nebula retained its cloud-like appearance. Its central region was bright and concentrated, yes, but the overall structure remained diffuse. Something about it was different from star clusters, different from gas clouds, different from anything astronomers had a clear category for. The real spark came with the development of photography in the late 1800s. Suddenly, astronomers could capture images of nebulae with long exposures, gathering light over hours in ways the human eye never could. When photographic plates were aimed at Andromeda and exposed for extended periods, a stunning structure emerged. The nebula was not simply a cloud. It had shape. It had form. Spiral arms, sweeping outward from a central core, became visible in the photographs. This was astonishing. Nebulae were not supposed to have such complex, organized structure. Gas clouds did not arrange themselves into elegant spirals. Star clusters did not have arms. The spiral shape was the key that unlocked everything. It suggested that whatever Andromeda was, it had rotation, it had dynamics, it had a structure that implied vast scales and long timescales. Some astronomers began to speculate that these spiral nebulae might be island universes, entire systems of stars far beyond the boundaries of the Milky Way. Others remained skeptical, arguing that everything visible in the sky must be part of our own galaxy. The debate intensified through the early 1900s. Observations multiplied. Some spiral nebulae showed motion, their arms appearing to rotate over years of observation, though later this was shown to be an artifact of measurement. Others showed evidence of individual bright spots that might be stars. The data was conflicting, the interpretations varied, and the question of what Andromeda truly was remained unresolved. Then came the development of spectroscopy, the technique of splitting light into its component wavelengths to reveal what objects are made of and how they move. When astronomers turned spectrographs toward Andromeda, they discovered something remarkable. The light from the nebula was blue-shifted. It was moving toward us at incredible speed, over 100 kilometers per second. This was extraordinary because most distant objects showed red shift, moving away as the universe expanded. But Andromeda was coming closer. This suggested it was not part of some expanding shell of gas or debris, but a distinct object with its own motion, bound gravitationally to our region of space. The blue shift added weight to the idea that Andromeda was separate, substantial, massive enough to move independently through the cosmos. But the definitive discovery, the moment when the mystery truly sparked into clarity, came in 1923. Edwin Hubble, working at the Mount Wilson Observatory with the largest telescope in the world at that time, the 100-inch Hooker telescope, began a systematic study of Andromeda. He took photograph after photograph, exposing plates for hours, searching for detail, and he found it. Within the spiral arms of Andromeda, Hubble identified individual stars. Not just any stars, but a specific type called Cepheid variables. These stars pulse in brightness with regular periods, and crucially, astronomers had recently discovered that the period of pulsation is directly related to the star's intrinsic brightness. This made Cepheids perfect for measuring distances. By observing how long it took a Cepheid to brighten and dim, you could calculate how luminous it truly was. Then, by comparing that true brightness to how faint it appeared from Earth, you could determine its distance. Hubble measured the periods of Cepheid variables in Andromeda. The calculations were meticulous, careful, repeated, and the result was staggering. The Cepheids were so distant that they could not possibly be within the Milky Way. Their distance was measured not in thousands of light-years, but in hundreds of thousands, eventually refined to over 2 million light-years away. With that single measurement, everything changed. Andromeda was not a nebula within our galaxy. It was another galaxy entirely, an island universe, just as some had speculated. The little cloud was vast, beyond comprehension, a separate system of stars comparable to or even larger than the Milky Way itself. The spark of mystery had been ignited, and it burned with implications that would reshape all of astronomy. If Andromeda was a galaxy, then what about the other spiral nebulae scattered across the sky? Were they galaxies too? The answer was yes. The universe was suddenly, dramatically larger. The Milky Way was not the cosmos. It was one galaxy among countless others, and Andromeda, the faint blur visible to the naked eye, was our nearest major neighbour. This discovery did not come from a single moment of insight, but from the accumulation of observations, each building on the last, from Al-Sufi noticing the blur, to Marius describing it through a telescope, to Herschel cataloguing it, to photographers revealing its spiral shape, to spectroscopists measuring its motion, to Hubble finally proving its distance. Each step was necessary. Each observer contributed a piece. And with that, the discovery, the question shifted. It was no longer, what is the Andromeda Nebula? It became, how big is the Andromeda Galaxy? What does it contain? How does it compare to our own? The mystery had not been solved. It had only deepened, opening doors to questions about scale, about structure, about the nature of galaxies themselves. The spark had been lit. Now it was time to explore what it illuminated. As you breathe slowly, let this moment settle. Imagine the excitement in Hubble's mind when the calculations came together. Imagine the shift in perspective when astronomers realized the universe was not a single galaxy, but a cosmos filled with them. Imagine standing beneath that faint blur, knowing now that it was not little at all but immense, and that you were seeing it across a gulf of space that light itself took millions of years to traverse. The discovery was both an ending and a beginning. An ending to centuries of uncertainty about what Andromeda was, a beginning to a new era of understanding, where galaxies became the fundamental structures of the universe, where distance was measured in millions of light years, where the true scale of creation began to reveal itself. And it all came from noticing a faint blur, asking what it was, and refusing to stop looking until the answer emerged. When Edwin Hubble announced his findings in 1924, presenting his evidence that Andromeda was a separate galaxy far beyond the Milky Way, the response from the astronomical community was not immediate acceptance, but a mixture of awe, skepticism, and profound disorientation. The scale of what he was proposing challenged everything astronomers thought they knew about the size of the universe. For decades, the prevailing view had been that the Milky Way was the universe. Everything visible in the night sky, every star, every nebula, every cluster, all of it was thought to be part of our galaxy. The idea was comfortable in a way. Vast, yes, but contained, comprehensible. At least in principle. The Milky Way stretched perhaps 100,000 light-years across, contained billions of stars, and that was immensity enough for most people to grasp, or at least to accept. Now Hubble was saying that the faint smudge in Andromeda, which had been assumed to be a relatively nearby cloud of gas or cluster of stars, was actually another Milky Way, another complete galaxy, sitting millions of light-years away. The implications were staggering. If Andromeda was a galaxy, then so were the other spiral nebulae. The universe was suddenly not one galaxy but countless galaxies, each separated by voids so vast that even light took millions of years to cross them. Some astronomers felt a sense of vertigo. The ground beneath their understanding had shifted. Harlow Shapley, one of the most prominent astronomers of the time, had argued forcefully that spiral nebulae were part of the Milky Way. He had even participated in the famous Great Debate of 1920, where he and Heber Curtis presented opposing views on the scale of the universe. Curtis had argued that spiral nebulae were island universes. Shapley had disagreed, believing the Milky Way encompassed everything. When Hubble's evidence emerged, Shapley was faced with being wrong about something fundamental. His initial reaction was reportedly one of reluctance. He questioned the measurements, wondered if there might be errors in the calculations, suggested alternative explanations. This was not stubbornness, but the natural response of a scientist whose worldview was being upended. To accept Hubble's findings meant accepting that the universe was far larger than he had believed, and that was not an easy thing to do. But the evidence was solid. Hubble had not relied on a single measurement. He had identified multiple Cepheid variables in Andromeda, measured their periods carefully, calculated distances using well-established methods. Other astronomers repeated his observations and confirmed his results. The distance was real. Andromeda was indeed a separate galaxy. As the evidence accumulated, awe began to replace skepticism. Astronomers started to grasp what this meant. The universe was not just bigger than they had thought. It was bigger in a way that required rethinking fundamental concepts. If galaxies were the building blocks of the cosmos, then what was the structure of the universe as a whole? How many galaxies were there? How far did they extend? Were there limits, or did they go on forever? The questions multiplied faster than the answers. Each new telescope, each new photograph, revealed more spiral nebulae, more galaxies, more evidence that the cosmos was filled with these island universes. The Milky Way was not special. It was ordinary, one among multitudes. Andromeda was not unique. It was one of many neighbours. The sheer scale of it was overwhelming. Public reaction, when the discovery filtered out beyond the scientific community, was equally mixed. Some people felt a sense of wonder. The universe was grander than anyone had imagined, filled with galaxies like grains of sand on a beach. Others felt a kind of existential unease. If the Milky Way was just one galaxy among billions, what did that mean for humanity's place in the cosmos? Were we even more insignificant than we had thought? Newspapers ran headlines trying to capture the magnitude of the discovery. The universe expands. New galaxies found beyond our own. Astronomers discover island universes. The language struggled to convey what was happening. How do you explain to someone that everything they thought was the universe is actually just one small part of something incomparably larger? For astronomers, the shift was both exciting and humbling. Exciting because it opened up entirely new fields of study. If galaxies existed, they could be classified, compared, their motions tracked, their properties measured. The universe had revealed itself to be a laboratory of unimaginable size. Humbling because it made clear how little they had known. For all the progress of science, for all the powerful telescopes and careful measurements, the basic structure of the universe had been misunderstood. Edwin Hubble himself was relatively restrained in his public statements. He presented the evidence clearly, let it speak for itself, and moved on to the next set of observations. But privately, he must have felt the weight of what he had discovered. In one stroke, he had changed humanity's understanding of the cosmos. The faint blur in Andromeda had become a key that unlocked the true scale of creation. There was also a sense of continuity. The discovery did not come from nowhere. It built on centuries of observation, on the work of countless astronomers who had catalogued, measured, and theorized. Al-Sufi had noticed the little cloud. Herschel had catalogued it. Photographers had revealed its spiral shape. Each had contributed. Hubble had simply been the one to bring all the pieces together and make the final measurement that proved what it was. In this way, the response to the discovery was not just awe and disbelief, but recognition. Recognition that science progresses through collaboration across generations, that answers come from patience and persistence, that the universe reveals itself slowly to those who keep looking. As the initial shock faded, astronomers began to adapt. They accepted that galaxies were the fundamental structures of the universe. They started measuring distances to other galaxies, mapping their distribution, studying their properties. The field of extragalactic astronomy was born. A discipline dedicated to understanding galaxies and the larger cosmos they inhabited. But the awe never fully went away. Even as galaxies became familiar objects of study, even as catalogues grew to include thousands and then millions of them, the fundamental wonder remained. Each galaxy was a city of stars, each star potentially hosting planets, each planet a possible cradle of life. The universe was not just large, it was filled with possibility, with complexity, with structures that boggled the mind. And Andromeda, The faint blur that started it all became a symbol of how much we had yet to learn, of how the universe constantly exceeds our expectations, of how something seemingly small can hide immensity. Every time an astronomer looked at it through a telescope, they were reminded of Hubble's discovery, of the moment when the universe expanded from one galaxy to countless galaxies. The disbelief eventually faded, but the awe remained. It remains still. Every time we look up and see that faint smudge in the sky, knowing now what it truly is, the response to discovering Andromeda's true nature was profound, because it changed not just astronomy, but our entire conception of our place in existence. We were not citizens of the universe. We were citizens of one galaxy among billions, looking out at neighbours across voids we could barely comprehend. And somehow, that made the cosmos more beautiful, not less, more wondrous, not less, more worthy of exploration, not less. The first response was awe and disbelief, but the lasting response has been curiosity, a desire to understand not just Andromeda, but all the galaxies beyond, to map the universe in all its immensity. Even after Edwin Hubble proved that Andromeda was a galaxy millions of light years away, a peculiar contradiction remained at the heart of the discovery, one that scientists struggle to reconcile, one that still invites wonder even today. How could something so unimaginably vast appear so impossibly small? The numbers themselves seem to war against each other. Andromeda stretched 220,000 light-years across its disk. It contained close to 1 trillion stars. Its mass, including the invisible dark matter surrounding it, was more than 1.5 trillion times the mass of our Sun. By any reasonable measure, it was one of the most immense structures in the local universe. And yet, to your eyes, it appears as nothing more than a faint smudge, a blur so modest that most people never notice it in their entire lives. Even when you know exactly where to look, even on the darkest nights far from city lights, it barely registers as more than a dim patch among the stars. You could cover it with your thumb held at arm's length. This tiny, fragile glow contains 1 trillion suns. This contradiction between immensity and appearance is not just a curiosity. It reveals something profound about the nature of the universe, about distance, about light, about the limits of human perception. Science can measure Andromeda, can count its stars, can calculate its mass, can predict its future. But science cannot fully resolve the paradox of how we experience it, how something so vast can feel so distant and small. The key to understanding this lies in distance itself. 2.5 million light-years is not just a number. It is a gulf so wide that it defies intuition. Light, travelling at 300,000 kilometers per second, the fastest speed in the universe, still takes 2.5 million years to cross that space. Every photon reaching your eyes tonight began its journey before your species existed, before any human walked upright, before our ancestors had descended from the trees. Distance dilutes light. Imagine a candle flame in a dark room. Up close, it is bright, warm, overwhelming. Step back a few meters and it becomes dimmer, cooler, less intense. The light has spread out over a larger area, so less of it reaches your eyes. Step back far enough and the flame becomes a faint point, barely visible. The flame itself has not changed. It still burns with the same intensity, but from far away, its light has scattered across such a vast sphere that only a tiny fraction reaches you. Now multiply that distance not by meters but by trillions of kilometers. Not by rooms but by the space between galaxies. Andromeda's trillion stars are all burning, all radiating light, but by the time that light reaches Earth, it has spread so thin that only the faintest whisper arrives. What should be a blaze becomes a blur. What should dominate the sky becomes barely visible. This is the science of it, the explanation that makes sense on paper. Inverse square law, light intensity decreasing with distance, straightforward physics. And yet, even understanding the science does not remove the mystery, because knowing why Andromeda appears faint does not change the feeling of standing beneath it, looking up, and being struck by the impossibility of seeing another galaxy with nothing but your eyes. The contradiction deepens when you consider that most of Andromeda is invisible. What you see, that faint core, is only a fraction of the galaxy's true extent. The spiral arms, filled with dust and gas and young blue stars, are too dim to register, without instruments. The outer halo, stretching perhaps twice as far as the visible disk, is composed of stars so faint and so spread out that they vanish into the darkness. If your eyes were sensitive enough, if you could gather light like a telescope does over hours of exposure, Andromeda would appear enormous, spanning an area several times larger than the full moon. But you cannot. Your eyes are limited. They collect light for a fraction of a second, not hours. They are sensitive to only a narrow range of wavelengths, missing the infrared glow of dust, the ultraviolet burn of young stars, the X-ray emissions from violent events. What you see is not Andromeda as it truly is, but a tiny subset of its reality, filtered through the limitations of human vision. And here is where mystery pushes back against science. Science can explain the mechanisms, can describe why the galaxy appears as it does. But mystery asks a different question. What does it mean that we can see it at all? What strange fortune allowed evolution to shape our eyes just sensitively enough to gather that faint glow? A little less sensitive, and Andromeda would be invisible to us, unknown until telescopes revealed it. A little more sensitive, and perhaps we would see not just Andromeda, but dozens of other galaxies scattered across the sky. We exist in a narrow window of perception, just barely able to glimpse our nearest galactic neighbour. Is that coincidence? Or does it say something about the universe, about the scales at which complexity and consciousness arise, about the relationship between what is there and what can be known? Science does not have answers to these questions. They drift beyond the realm of measurement into philosophy, into contemplation. And that is part of the contradiction. Andromeda is both knowable and unknowable. We can measure it precisely, calculate its mass, track its motion, predict its collision with the Milky Way billions of years from now. But we cannot fully grasp the immensity remains just beyond reach, always slightly too large to hold in thought. There is also a temporal contradiction. The light you see from Andromeda is ancient, 2.5 million years old. You are seeing the galaxy not as it is now, but as it was in the deep past. During the time that light has been travelling, stars within Andromeda have been born and have died. Planets have formed, perhaps civilizations have risen and fallen, but you see none of that. You see only the past, frozen in the photons that happen to arrive tonight. And yet, Andromeda continues. Right now, in a present you cannot access, the galaxy exists, evolves, changes. There is an Andromeda as it is tonight, but you will not see it for another 2.5 million years. The one you see is a ghost, a memory written in light. Science can account for this. Light takes time to travel. Delay is inevitable. But mystery whispers that you are always looking backward, that the universe you see is always the universe that was, never the universe that is. This contradiction between past and present, between what was and what might be now, adds another layer to the question of size. How big is Andromeda? As it was 2.5 million years ago, or as it is now? The answer depends on which Andromeda you mean, the one you can see, or the one that exists beyond your perception, continuing its story in a present you cannot reach. Science and mystery do not oppose each other here. They dance together, each revealing something the other cannot. Science gives us precision, measurement, understanding. Mystery gives us wonder, perspective, humility. Together, they create the full picture of what Andromeda is. As your breathing deepens and your thoughts begin to drift, hold this contradiction gently. Andromeda is immense, and it appears small. It is ancient, and it is present. It is knowable, and it remains mysterious. These contradictions are not problems to solve, but realities to accept. Part of what it means to exist in a universe where scales stretch beyond comprehension. The galaxy is there, whether we understand it or not, whether we see all of it or only a fragment. And perhaps that is enough. Perhaps the contradiction is part of the gift. the reminder that the universe is always larger, stranger, more complex than we can fully grasp. Science reaches toward it. Mystery holds space for what cannot be measured. And Andromeda, patient and ancient, continues to shine, waiting for the next observer to look up and wonder. Once Edwin Hubble established that Andromeda was a separate galaxy, the question of its true size became urgent. But measuring a galaxy 2.5 million light-years away is not a simple task. Different methods produce different results. Different assumptions led to different conclusions. And so, even as astronomers agreed that Andromeda was a galaxy, they disagreed, sometimes sharply, about exactly how big it was. The first major division came from the method of measurement itself. Hubble had used Cepheid variable stars to determine Andromeda's distance, and from distance he could estimate size. But the calibration of Cepheids, the relationship between their pulsation period and their true brightness, was not as precise as astronomers had hoped. Small errors in calibration led to large errors in distance, and therefore in size. Some astronomers argued that Andromeda was roughly the same size as the Milky Way, perhaps 100,000 light-years across. This made sense to them. If galaxies were the fundamental structures of the universe, perhaps they came in a standard size, shaped by similar processes of formation. The Milky Way and Andromeda, as the two largest galaxies in the local group, might be twins, comparable in mass and extent. Others disagreed. When they looked at the apparent size of Andromeda in the sky and combined it with distance measurements, they arrived at a larger figure. Perhaps Andromeda was 150,000 light-years across, perhaps even 200,000. This would make it significantly larger than the Milky Way, the dominant galaxy in the local group. The disagreement was not merely academic. It had implications for understanding how galaxies formed, how they evolved, whether they grew over time or remained relatively constant. If Andromeda was larger, it might have formed earlier, or it might have absorbed more smaller galaxies. If it was the same size as the Milky Way, perhaps galactic formation followed predictable rules that created similar structures regardless of location. Observations complicated matters further. When astronomers measured the rotation of stars and gas in Andromeda, they found that the outer regions were moving faster than expected. According to the laws of gravity, objects farther from the center of a rotating system should move more slowly, just as planets farther from the Sun orbit more slowly. But in Andromeda, and in other galaxies, the rotation curves stayed flat, even at great distances from the core. This suggested one of two things. Either the laws of gravity needed to be modified at galactic scales, or there was additional mass in the galaxy that could not be seen. Most astronomers favoured the second explanation. There must be invisible matter, dark matter, surrounding the galaxy and extending far beyond the visible disk. This dark matter would provide the gravitational pull needed to keep the outer stars moving quickly. But if dark matter existed, how much was there? And how far did it extend? Some theories suggested that the dark matter halo around Andromeda might stretch twice as far as the visible galaxy. Others proposed even larger halos, extending millions of light-years into space. If the halo was included in the measurement of size, then Andromeda was not 200,000 light-years across, but perhaps 1 million light-years or more. This created a philosophical problem as much as a scientific one. What counted as the galaxy? Only the visible stars, the stars plus the gas and dust, the entire structure including the dark matter halo. Different definitions gave wildly different answers to the question of size. Another division emerged around the question of mass. Early estimates suggested Andromeda might contain 200 billion stars, roughly half the number in the Milky Way. But as observations improved, those estimates were revised upward. Perhaps Andromeda had 400 billion stars, perhaps 600 billion. By the early 2000s, estimates had climbed to nearly 1 trillion stars, more than double the number in the Milky Way. Each revision changed not just the star count, but the understanding of Andromeda's role in the local group. If it was the heavyweight, then its gravity dominated. The Milky Way and other galaxies would be satellites, in a sense, orbiting around or influenced by Andromeda's pull. But if the two galaxies were more evenly matched, then the dynamic was different, more balanced, a dance between equals rather than a dominant partner and lesser companions. The theories divided not just between individuals but between schools of thought. Some astronomers favoured conservative estimates, preferring to work with confirmed measurements and avoid speculation. Others embraced larger estimates, arguing that the faintness of distant structures meant much of the galaxy remained undetected. Both groups had evidence, both had arguments. Neither could definitively prove the other wrong. Technology slowly resolved some disputes. Better telescopes revealed fainter stars, pushing the visible extent of Andromeda farther outward. Deep surveys detected streams of stars in the halo, remnants of smaller galaxies Andromeda had consumed. Radio telescopes mapped the distribution of hydrogen gas, showing that it extended well beyond the optical disk. Infrared observations revealed dust structures invisible to optical telescopes. Each new wavelength, each new instrument, added data. But adding data did not always settle debates. Sometimes it created new questions. The discovery of rings of dust around Andromeda, for example, suggested past interactions with companion galaxies. But when had those interactions occurred? How much mass had been added? Did that make Andromeda larger now than it had been in the past, or had it always been massive? The question of comparison also divided minds. Some astronomers were content to measure Andromeda in isolation, determining its properties without reference to other galaxies. Others insisted that comparison was essential. Andromeda had to be understood in the context of the local group, in the context of spiral galaxies generally, in the context of the cosmic web. Its size was meaningful only in relation to other structures. This comparative approach led to classifications. Andromeda was a spiral galaxy, specifically a type SA or SB spiral, depending on the classification scheme used. It had a large bulge, broad spiral arms, a relatively smooth disk. These characteristics placed it in a category with other galaxies of similar morphology. But did that mean it was typical of its class, or was it an outlier, unusually large or unusually massive? Different answers suggested different histories. If Andromeda was typical, then understanding it meant understanding spiral galaxies in general. If it was unusual, then its history might be unique, shaped by specific events or circumstances that did not apply elsewhere. Through all these debates, one thing remained clear. Andromeda was large by any measure. Whether it was 100,000 or 200,000 or 1,000,000 light-years across, whether it contained 200 billion or 1 trillion stars, whether its mass was comparable to the Milky Way's or significantly greater, it was immense. The debates were about degrees of immensity, not about whether the galaxy was big. And perhaps that is the most important realization. The theories divided, the minds disagreed, but all of them were grappling with the same fundamental truth. Andromeda was vast beyond everyday comprehension. The exact numbers mattered for science, for models, for predictions. But for the rest of us, for those standing beneath the night sky and seeing that faint blur, the theories are less important than the shared recognition of scale. As you settle deeper into stillness, let the disagreements fade. Let the numbers blur. What remains is the essential fact. Andromeda is big. Bigger than mountains, bigger than planets, bigger than solar systems, bigger than the distance light travels in human lifetimes. It is big in a way that makes precise measurement almost beside the point. The theories may divide, but the wonder unites. And that wonder is what carries you into sleep, gently, patiently, under the glow of 1 trillion distant suns. Understanding the true size of Andromeda required more than a single measurement, or a moment of insight. It demanded decades of patient pursuit, countless nights at telescopes, photographs stacked upon photographs, calculations refined and recalculated. The investigation became one of the great ongoing projects of 20th century astronomy. Drawing in researchers from around the world, each adding their own piece to the puzzle, the pursuit began in earnest after Hubble's discovery. Once astronomers knew that Andromeda was a separate galaxy, the race was on to understand everything about it. How wide did it extend? How massive was it? What was its composition? How did it compare to the Milky Way? Every question led to more questions, and answering them required developing new techniques, new instruments, new ways of seeing. The first challenge was improving distance measurements. Hubble's Cepheid method had proven that Andromeda was millions of light-years away, but the exact distance remained uncertain. Small errors in the calibration of Cepheid variables, in the understanding of how their brightness related to their period, could throw off calculations by hundreds of thousands of light-years, and distance was the foundation of everything else. Get the distance wrong, and every other measurement, size, mass, luminosity, would be wrong too. Astronomers returned to Andromeda again and again with better telescopes, more sensitive photographic plates, longer exposures. They identified more Cepheid variables, dozens of them, measuring each one carefully. They developed statistical methods to reduce uncertainty, averaging multiple measurements, accounting for errors. Slowly, the distance estimate became more precise. Not 2 million light-years, but closer to 2.5 million. Not 2.5 million, but 2.54 million. Each refinement brought them closer to the truth. But distance alone was not enough. To measure the galaxy's width, astronomers needed to trace its extent, to find where the stars ended and empty space began. This was harder than it sounds. Galaxies do not have sharp edges. They fade gradually, stars becoming sparser and sparser until they blend into the background. Where do you draw the line? At what surface brightness do you say here the galaxy ends? Different astronomers made different choices. Some traced the bright spiral arms, measuring from the core to the outermost visible structures. This gave a relatively compact size, perhaps 150,000 light-years. Others looked for faint stars in the halo, pushing the measurements farther out to 200,000 light-years or more. Still others argued that the true extent should include the dark matter halo, invisible but detectable through its gravitational effects. The pursuit of size became a pursuit of different kinds of measurements. Optical telescopes revealed the distribution of stars. Radio telescopes mapped neutral hydrogen gas, which extended beyond the visible disk. X-ray telescopes found hot gas and the signatures of violent events. Infrared telescopes penetrated dust clouds, revealing hidden structures. Each wavelength told a different story about where Andromeda's influence reached. One breakthrough came from studying the galaxy's rotation. By measuring how fast stars and gas moved at different distances from the centre, astronomers could infer the distribution of mass. In the 1970s, Vera Rubin and Kent Ford conducted groundbreaking observations of rotation curves in spiral galaxies, including Andromeda. What they found was surprising. Stars in the outer regions were moving just as fast as those closer in, sometimes even faster. This should not have been possible if only visible matter was present. The conclusion was inescapable. There had to be additional mass, dark matter, forming a halo around the galaxy. And this halo had to be massive, outweighing the visible stars by a factor of 5 or 10 to 1. Suddenly, the question of Andromeda's size became even more complex. The visible galaxy might be 200,000 light-years across, but the dark matter halo could extend twice as far or farther. In a real sense, Andromeda was much larger than anyone could see. Pursuing this invisible component became its own field of study. Astronomers used gravitational lensing, the bending of light from background objects by Andromeda's mass, to map where the dark matter was concentrated. They studied the motions of satellite galaxies orbiting Andromeda, using those motions to estimate the total mass enclosed within their orbits. They ran computer simulations of galaxy formation, trying to understand how much dark matter was needed to create a structure like Andromeda. Each approach gave slightly different answers, but all pointed to the same conclusion. Andromeda was embedded in a vast halo of invisible matter, and that halo was an essential part of the galaxy's structure. To ignore it would be to misunderstand what the galaxy truly was. The pursuit also required international collaboration. Andromeda is visible from both the northern and southern hemispheres, though best seen from the north. Observatories in California, Arizona, Chile, Hawaii, Spain, and elsewhere all turned their instruments toward it. Data from one telescope was compared with data from another. Techniques developed at one observatory were shared and refined by others. The investigation became a collective effort, astronomers building on each other's work, correcting each other's errors, pushing toward ever greater precision. Space-based telescopes added a new dimension. The Hubble Space Telescope, launched in 1990, was able to observe Andromeda without the blurring effect of Earth's atmosphere. Its images were extraordinarily sharp, resolving individual stars with unprecedented clarity. In 2012 and 2015, Hubble was used to create massive photographic mosaics of Andromeda. Images containing over 1 billion pixels, showing more than 100 million stars individually. These images were revelations. For the first time, astronomers could see the structure of Andromeda in exquisite detail. Star clusters, nebulae, dust lanes, all were visible with a clarity that earlier generations could only dream of. The mosaics allowed researchers to study not just the galaxy as a whole, but individual regions within it, tracing the patterns of star formation, the distribution of different stellar populations, the architecture of the spiral arms. But even these stunning images had limits. They showed the visible galaxy, the stars that shine in optical light. They could not reveal the dark matter halo, could not show the full extent of the hydrogen gas, could not capture the high-energy processes visible only in X-rays. The pursuit continued, layering observations from different instruments, building a composite picture that included every wavelength, every type of measurement. Another line of investigation focused on Andromeda's history. How had it grown to its current size? Had it always been large? Or had it accumulated mass over billions of years? Astronomers found evidence of past mergers, streams of stars torn from smaller galaxies that Andromeda had consumed. These tidal streams wrapped around the main galaxy, visible as faint arcs in deep images. By mapping them, by studying their chemistry and ages, researchers could reconstruct Andromeda's growth history. It became clear that Andromeda had not been born large. It had grown through mergers and accretion, pulling in smaller companions, adding their stars and gas to its own. Each merger left scars, disturbances in the disk, asymmetries in the spiral arms. The galaxy was not a static structure but a dynamic one, constantly evolving, constantly adding to itself. This realization shifted the question of size once again. If Andromeda was still growing, then its current size was only a snapshot, a temporary state in an ongoing process. In billions of years, after it merged with the Milky Way, it would be even larger. Size was not fixed, but fluid, changing over cosmic time. The pursuit of understanding Andromeda's size became, in a way, the pursuit of understanding galaxies themselves. Every technique developed to measure Andromeda was applied to other galaxies. Every insight gained was tested against other systems. Andromeda was close enough to study in detail, and that detail informed theories of how all galaxies formed and evolved. As the decades passed, the measurements became more refined. Uncertainties shrank, confidence grew. By the early 21st century, astronomers had converged on a consensus. Andromeda's visible disk was approximately 220,000 light-years across. Its mass, including dark matter, was roughly 1.5 trillion solar masses. It contained close to 1 trillion stars. These were not final answers. They would continue to be refined, but they were solid enough to build on. The pursuit had not ended. It never truly ends, but it had reached a new phase. The basic parameters were established. Now the focus shifted to understanding the details. The structure within the galaxy, the processes driving star formation, the interactions with satellites, the preparation for the eventual merger with the Milky Way. And through it all, Andromeda remained patient. It did not hurry. It did not reveal itself all at once. It waited for each generation of astronomers to develop the tools, the techniques, the understanding needed to see a little more clearly. The pursuit was human, the urgency was human, but the galaxy itself simply continued, orbiting, evolving, shining across the void. As you breathe deeply and feel your body settling, think of those astronomers, night after night at their telescopes, photograph after photograph, calculation after calculation. The pursuit of knowledge is patient too, built not on sudden breakthroughs alone, but on steady accumulation. Each measurement mattered, each observation added a piece, and together they built a picture of immensity that we can now hold in thought, even as we drift towards sleep. All the theories, all the debates, all the passionate pursuit would mean nothing without data. Cold, hard measurements extracted from light, translated into numbers, verified and cross-checked. The understanding of Andromeda's size rests not on speculation but on evidence, on actual observations that can be repeated, tested, and confirmed. The data is the foundation, the bedrock upon which everything else is built. The most fundamental piece of data is distance. Without knowing how far away Andromeda is, no other measurement makes sense. The distance determines how large something appears in the sky, translates into its actual physical size. An object appearing small could be tiny and nearby, or enormous and distant. Only by measuring distance can you distinguish between these possibilities. The primary method for determining Andromeda's distance remains Cepheid variable stars. These are massive, luminous stars that pulse in brightness with regular periods, typically ranging from a few days to several months. The physics behind the pulsation is well understood. As the star expands and contracts, its brightness rises and falls in a predictable pattern. And crucially, the period of pulsation is directly related to the star's intrinsic luminosity. A Cepheid with a longer period is more luminous than one with a shorter period. This relationship, known as the period-luminosity relation, was discovered by Henrietta Swan-Leavitt in the early 1900s. By observing Cepheids in the Small Magellanic Cloud, she found that brighter Cepheids had longer periods. Once this relationship was calibrated, it became a powerful tool for measuring distances. Find a Cepheid, measure its period, calculate how luminous it truly is, compare that to how bright it appears from Earth, and the distance follows from straightforward mathematics. Edwin Hubble identified dozens of Cepheids in Andromeda in the 1920s. Modern telescopes, particularly the Hubble Space Telescope, have identified hundreds more. Each measurement refines the distance estimate. The current best value places Andromeda at approximately 2.54 million light-years away, with an uncertainty of only a few %. That distance serves as the anchor for everything else. Knowing it, astronomers can measure Andromeda's angular size in the sky, how many degrees or arc-minutes it spans, and convert that into physical size. The galaxy's disk extends roughly 3 degrees across at its widest, about 6 times the apparent diameter of the full moon. At a distance of 2.54 million light-years, that angular size corresponds to a physical diameter of approximately 220,000 light-years. But size measurements depend on what you count as the galaxy. The bright central bulge is much smaller, perhaps 20,000 light-years across. The spiral arms extend farther, out to 110,000 light-years from the centre on either side. Beyond the main disk, faint stars in the halo stretch even farther, detected only in the deepest surveys. Photometric data, measurements of brightness, provide clues to the total number of stars. By measuring the total light output of Andromeda and comparing it to models of stellar populations, astronomers estimate that the galaxy contains between 800 billion and 1 trillion stars. The uncertainty comes from not knowing the exact mix of star types. Low-mass red dwarfs are faint but numerous. High-mass blue giants are bright but rare. Different assumptions about the distribution lead to different star counts. Spectroscopic data, measurements of light split into its component wavelengths, reveal Andromeda's motion. The entire galaxy shows a blue shift, meaning its light is compressed toward shorter wavelengths. This indicates that Andromeda is moving toward us at approximately 110 kilometers per second. This velocity, combined with its distance, allows astronomers to predict that Andromeda and the Milky Way will collide in roughly 4 billion years. Rotation curves, Graphs showing how fast stars and gas move at different distances from the galactic center provide evidence for dark matter. In a system where all the mass is visible, objects farther out should move more slowly, following Kepler's laws of orbital motion. But in Andromeda, as in most galaxies, the rotation curve stays flat or even rises slightly at large distances. This means there must be additional mass beyond what we can see, distributed in a halo surrounding the visible disk. Estimates of Andromeda's total mass, including dark matter, range from 1.2 to 1.9 trillion solar masses. The uncertainty reflects the difficulty of measuring something invisible. Astronomers infer the dark matter's presence from its gravitational effects, but the exact distribution remains uncertain. Multi-wavelength observations add layers to the data. Optical images show the distribution of stars. Infrared observations from telescopes like Spitzer and Herschel reveal warm dust glowing at longer wavelengths. These images show structures invisible in optical light, including rings and clumps of dust that may have formed from past interactions with satellite galaxies. Radio observations at 21 centimeters, the emission line of neutral hydrogen, map the distribution of cold gas. This gas extends beyond the optical disk, forming a reservoir of raw material for future star formation. The total mass of hydrogen in Andromeda is estimated at several billion solar masses, a significant fraction of the baryonic or normal matter in the galaxy. X-ray observations from telescopes like Chandra reveal high-energy processes. Point sources of X-rays mark neutron stars and black holes accreting matter from companion stars. Diffuse X-ray emission traces hot gas heated by supernova explosions. At the center of Andromeda, faint X-ray emission marks the location of its supermassive black hole, a monster weighing approximately 100 million solar masses. The black hole's mass was determined by studying the motions of stars near the galactic center. These stars orbit at tremendous speeds, thousands of kilometers per second, whipping around the central region in tight elliptical paths. Only an extremely massive, compact object could hold them in such orbits. By mapping these stellar velocities and applying the laws of gravity, astronomers calculated that the central black hole must weigh roughly 100 million times as much as the Sun. Surveys of star clusters within Andromeda provide data on the galaxy's age and chemical composition. Globular clusters, dense spherical collections of old stars, orbit in the halo. By measuring the ages of stars in these clusters, astronomers estimate that Andromeda began forming stars more than 10 billion years ago, not long after the universe itself began. Chemical abundance measurements, determining how much of various elements are present in Andromeda's stars, tell a story of enrichment over time. Early generations of stars contained only hydrogen and helium, the elements created in the Big Bang. When these stars died, often in supernova explosions, they scattered heavier elements into space. Subsequent generations of stars formed from gas enriched with carbon, oxygen, iron, and other elements. By measuring these abundances, astronomers can trace the history of star formation and element production in Andromeda. Deep photographic surveys have revealed tidal streams, long arcs of stars that wrap around Andromeda. These are the remnants of smaller galaxies that were torn apart by tidal forces as they passed too close. The streams are faint, requiring long exposures and careful data processing to detect, but they provide direct evidence that Andromeda has grown by consuming its neighbours. One of the most striking pieces of data comes from the Hubble Space Telescope's multi-year survey of Andromeda. The Panchromatic Hubble Andromeda Treasury, or PHAT survey, observed a large swath of the galaxy in multiple wavelengths, creating images with over 1.5 billion pixels. These images resolved more than 100 million stars individually, allowing astronomers to study the galaxy's structure in unprecedented detail. The PHAT data revealed clustering patterns in young stars, showing where star formation is currently active. It showed the distribution of different stellar populations, young blue stars in the spiral arms, older red stars in the bulge and halo. It allowed precise measurements of the galaxy's distance by identifying thousands of Cepheid variables and other standard candles. All of this data, optical, infrared, radio, X-ray, near, and far, builds a composite picture. Andromeda is not a simple object, but a complex system with many components. The visible disk of stars, the dark matter halo, the gas reservoirs, the dust clouds, the star clusters, the satellite galaxies, the tidal streams, all are part of the whole. The data captures fragments of this complexity, clues that astronomers piece together like a vast puzzle. But data is never perfect. Every measurement has uncertainty. Every observation is subject to limitations. Light is absorbed by dust, making some regions harder to see. Faint structures require long exposures and careful calibration. Distance measurements depend on chains of inference, each link introducing potential error. This is why astronomers use multiple methods, cross-checking one against another. Cepheid variables give one distance estimate. The brightness of red giant stars gives another. The properties of globular clusters give a third. When multiple independent methods converge on similar answers, confidence grows. The data on Andromeda is now extensive enough that major surprises are unlikely. The basic parameters are well established, but refinements continue. New observations add detail. New techniques probe previously inaccessible regimes. The data will never be complete, but it is solid enough to build on. As you sink deeper into rest, let the data fade into abstraction. The numbers are real, the measurements are precise, but for sleep you do not need to hold them. What remains is the assurance that understanding is possible, that even something as vast as Andromeda can be measured, can be known, at least in part. The data is the bridge between mystery and knowledge, between wonder and understanding. And tonight, it carries you gently across, from question to answer, from wakefulness to dreams. Just when astronomers thought they understood Andromeda's size, when the measurements seemed to converge on solid numbers, a deeper mystery emerged. One that transformed not just the understanding of this one galaxy, but of all galaxies, of the universe itself. The visible stars, the bright spiral arms, the glowing core, all the structures that telescopes could photograph turned out to be only a small fraction of what was really there. The hidden truth was dark matter. The story began with observations that did not make sense. When astronomers measured how fast stars and gas orbited within Andromeda, they found something impossible. Objects at the outer edges of the galaxy were moving just as quickly as those closer to the centre. According to Newtonian physics, according to everything known about gravity, this should not happen. In systems held together by gravity, whether planets orbiting a star or stars orbiting a galactic centre, velocity should decrease with distance. The farther out you go, the slower the orbit should be. This pattern holds in the solar system. Mercury orbits the Sun at 48 kilometers per second. Earth at 30. Neptune at just 5. The relationship is precise, mathematical, predictable. Mass concentrated in the centre means faster orbits close in, slower orbits farther out. But galaxies do not follow this pattern. In Andromeda, as in the Milky Way, and nearly every other galaxy studied, the rotation curve stays flat. Stars hundreds of thousands of light-years from the core orbit at roughly the same speed as those much closer in. If only visible matter was present, these outer stars should be moving so slowly that they would take far longer to complete an orbit, or they should be flung out of the galaxy entirely, unable to remain bound. Yet they remain. The galaxies hold together. Something was providing additional gravitational pull, keeping those outer stars in their swift orbits, and that something had to be massive, far more massive than all the visible stars combined. The conclusion, first seriously proposed in the 1970s and confirmed through decades of subsequent observations, was that galaxies are embedded in halos of invisible matter. Matter that does not emit light, does not absorb light, does not interact with electromagnetic radiation in any way. Matter that makes itself known only through gravity. Dark matter. For Andromeda, this revelation was profound. The galaxy that appeared to stretch 220,000 light-years across invisible light was actually much larger. The dark matter halo extended perhaps twice as far, possibly even farther, reaching out into the space between galaxies. The visible disk was like an island floating in a much larger invisible ocean. Estimates of Andromeda's dark matter content vary. but most suggest that dark matter outweighs visible matter by a factor of at least 10 to 1. If Andromeda's stars and gas total perhaps 150 billion solar masses, the dark matter halo must contain over 1 trillion solar masses. The galaxy you can see is less than 10% of what is actually there. This hidden truth changed the meaning of size. When you ask how big Andromeda is, do you mean the visible part or the total structure? If you include the dark matter halo, Andromeda might stretch nearly 500,000 light-years across, possibly more. Its gravitational influence extends even farther, affecting the motions of satellite galaxies millions of light-years away. The nature of dark matter remains one of the great unsolved mysteries of physics. Astronomers know it is there. They can map its distribution by measuring its gravitational effects, but they do not know what it is made of. It is not ordinary matter, not protons and neutrons and electrons. It does not form atoms, does not shine, does not interact, except through gravity. Various candidates have been proposed. Perhaps dark matter consists of exotic particles left over from the early universe, particles that rarely interact with normal matter but exist in vast quantities. Perhaps it is primordial black holes, formed in the first moments after the Big Bang. Perhaps it is something stranger still, something current physics has not yet imagined. Whatever it is, it shapes galaxies. Computer simulations show that without dark matter, galaxies like Andromeda could not have formed. In the early universe, dark matter clumped together first, creating gravitational wells. Normal matter, gas and dust, fell into these wells, accumulating in the centres, forming stars. The visible galaxy is built on a scaffold of dark matter, a hidden architecture that determines the structure. This means Andromeda's true shape is not just the spiral you see in photographs. The true shape includes the dark matter halo, roughly spherical, extending far beyond the disk. The spiral is embedded within this sphere, like a coin suspended in a beach ball. Most of the galaxy's mass is in the halo. Most of its volume is dark. Detecting dark matter directly remains impossible with current technology, but its presence can be inferred through multiple lines of evidence. Rotation curves are one, gravitational lensing is another. When light from distant galaxies passes near Andromeda, it is bent by the gravity of all the matter in between, visible and dark. By measuring how much the light bends, astronomers can calculate the total mass causing the deflection. The motions of Andromeda's satellite galaxies provide yet another clue. Small galaxies like M32 and M110 orbit Andromeda, held in place by its gravity. By tracking their orbits, by measuring their velocities, astronomers can determine how much mass must be enclosed within their paths. The answer is always more than the visible stars and gas can account for. Dark matter fills the gap. There is also evidence from cosmology, from the study of the universe as a whole. The cosmic microwave background, the afterglow of the Big Bang, shows patterns imprinted by dark matter's gravitational influence in the early universe. The large-scale structure of galaxies, how they cluster and form filaments, also requires dark matter to explain. Andromeda's dark matter halo is not unique. It is part of a universal phenomenon. The hidden truth is humbling. For all the sophistication of modern telescopes, for all the data collected, the majority of Andromeda remains invisible. We see the bright part, the showy part, the part that emits light, but the bulk of the galaxy hides in darkness, detectable only through its gravitational fingerprint. This realization deepens the question of size. Andromeda is big in ways we can see, 220,000 light-years of stars and gas. But it is also big in ways we cannot see, a halo of dark matter perhaps 1,000,000 light-years across. Both are real, both are part of the galaxy, and neither can be fully understood without the other. The deeper mystery extends beyond just size. Dark matter also shapes the galaxy's evolution. When smaller galaxies are absorbed into Andromeda, they bring their own, dark matter halos with them. These halos merge, adding to Andromeda's mass, reshaping its gravitational field. The tidal streams of stars visible in deep images are accompanied by invisible streams of dark matter. Traces of the halos that once surrounded those consumed galaxies. Understanding this has implications for the future. When Andromeda and the Milky Way collide in 4 billion years, it will not just be their stars and gas that merge. Their dark matter halos will merge too, creating an even larger invisible structure. The resulting galaxy will be dominated by dark matter, just as its progenitors are. There is something almost poetic about this hidden truth. We look at Andromeda and see beauty, spirals of light, clouds of glowing gas, clusters of bright stars. But beneath and beyond that beauty lies something we cannot see, something that holds it all together. The visible galaxy floats in an invisible embrace, shaped and sustained by matter. We can detect, but not observe, directly. As your thoughts grow quieter and your breathing slows, let this mystery settle. You do not need to understand dark matter to appreciate its presence. You do not need to see the halo to know it is there. Andromeda is both visible and invisible, both known and mysterious. The deeper truth does not erase the surface beauty. It adds to it, layers upon layers, complexity upon complexity. The galaxy is larger than it appears, more massive than it seems, more mysterious than measurements alone can capture. And perhaps that is fitting. Perhaps galaxies, like the universe itself, should always hold secrets, always have depths that remain just beyond reach. The hidden truth is part of what makes Andromeda endlessly fascinating, endlessly worthy of study, endlessly capable of inspiring wonder. There comes a moment in every great scientific story when understanding shifts fundamentally, when the old framework no longer works and a new one must be built. For the study of Andromeda, and for the understanding of galaxy size in general, that turning point arrived when astronomers realized they were not just measuring stars, they were measuring entire ecosystems, complex systems where visible matter was only the tip of the structure. The paradigm shift happened gradually, but its effects were revolutionary. Before, a galaxy was thought of as a collection of stars, held together by their mutual gravity, slowly evolving over time. Simple in concept, if not in detail, measure the stars, count them, weigh them, and you know the galaxy. After the shift, galaxies became something far more complex. They were dynamic systems embedded in dark matter halos, constantly exchanging material with their surroundings, growing through mergers, shaped by invisible forces. The visible part was important, but it was only one component of a much larger whole. Size was no longer just about how far the stars extended. It was about the reach of gravitational influence, about the full extent of the dark matter halo, about the network of satellites and streams that made each galaxy not an isolated object, but a system. This shift transformed how astronomers thought about Andromeda specifically. It was not simply larger than the Milky Way in terms of stars. It was fundamentally more massive when dark matter was included, perhaps by 30 to 50%. That extra mass gave it stronger gravity, allowed it to hold more satellites, extended its influence farther into space. Andromeda was not just our neighbour. It was the dominant galaxy of the local group, the gravitational anchor around which other galaxies, including our own, danced. The realization also changed predictions about the future. The eventual collision between Andromeda and the Milky Way was already known, predicted from measurements of their relative motion. But with the understanding of dark matter, the collision became more complex. It would not just be stars passing through stars, as earlier models suggested. It would be dark matter halos merging, their gravitational fields interacting in ways that would reshape both galaxies fundamentally. Computer simulations of the collision, run with increasingly sophisticated models that included dark matter, showed that the merger would be violent in gravitational terms, even if stars themselves rarely collided. The dark matter halos would merge first, their interaction stirring the visible disks, pulling stars into tidal tails, triggering bursts of star formation as gas clouds collided and compressed. Over billions of years, the two spirals would become one giant elliptical galaxy, its stars distributed in a smooth, roughly spherical halo, its spiral structure erased by the chaos of merger. Understanding this process required a paradigm shift, not just in how astronomers thought about size, but in how they thought about galactic identity. Andromeda was not a static structure with a fixed size. It was a phase in an ongoing process of cosmic evolution. It had been smaller in the past, built up through countless mergers with dwarf galaxies. It would be larger in the future, combined with the Milky Way into something new. Size was not constant but dynamic, changing across cosmic time. This perspective also changed how astronomers classified galaxies. The old system, based primarily on shape, spirals and ellipticals and irregulars, remained useful for describing appearances. But a deeper classification emerged, based on mass and environment and history. Galaxies were grouped not just by how they looked, but by how they formed, how they evolved, where they lived in the cosmic web. Andromeda, in this new framework, was recognized as a relatively rare type, a massive spiral, still actively forming stars, in a relatively quiet region of space, not part of a large cluster where interactions would be more frequent and violent. Its size and mass placed it among the largest galaxies in the nearby universe, not the absolute largest, but well above average. Understanding why it grew so large, what circumstances allowed it to accumulate so much mass, became a key question. The paradigm shift also connected galaxies to cosmology, to the study of the universe's origin and evolution. Dark matter was not just a galactic phenomenon, it was a universal one. Simulations of cosmic structure formation showed that dark matter clumped into filaments and nodes, creating a cosmic web. Galaxies formed at the intersections of these filaments, where dark matter was most concentrated. Andromeda sat in one such node, its size and mass a direct consequence of its position in the cosmic web. This connected the question of how big Andromeda is to the question of why it is that big. Its size was not random but determined by its formation history, by the amount of dark matter in its region of space, by the smaller galaxies it had absorbed. Understanding size meant understanding history, and understanding history meant tracing back through billions of years of cosmic evolution. For students of astronomy, for those trying to make sense of galaxies, the paradigm shift was both clarifying and disorienting. Clarifying because it provided a framework that explained observations, that connected different pieces of evidence into a coherent whole. Disorienting because it revealed how much remained unknown, how many assumptions had been wrong, how much more complex reality was than earlier models suggested. The shift also had philosophical implications. If most of the universe was made of dark matter, invisible and mysterious, what did that say about our ability to understand the cosmos? We were like people trying to understand a building while only able to see the furniture inside, unaware of the walls and foundations that actually held it up. The visible universe was real, but it was only part of the story. For Andromeda, the turning point meant that every measurement had to be reconsidered. How big is it? The visible disk is 220,000 light-years across. The dark matter halo extends perhaps 1,000,000 light-years. Its gravitational influence reaches millions of light-years farther. Which number is the right answer? All of them, in different contexts. Size had become multifaceted, depending on what you were measuring and why. This complexity was not a failure of science, but a success. It meant understanding had deepened, that reality was being captured more accurately, that the questions being asked were more sophisticated. The paradigm shift was not an ending, but a beginning, opening up new avenues of research, new questions to ask, new mysteries to solve. As you rest now, feeling your body grow heavy, let this shift wash over you gently. The universe is more complex than it first appears. Galaxies are not simple objects, but intricate systems. Size is not a single number, but a constellation of measurements, each revealing a different aspect of truth. The turning point in understanding, Andromeda was realizing that what you see is only part of what is there, and that the invisible parts matter just as much as the visible. This is the nature of science, of knowledge itself. Each answer reveals new questions. Each solution opens new mysteries. The paradigm shift for Andromeda was not the end of inquiry, but its deepening, a recognition that the galaxy held layers upon layers of complexity, that understanding would be a journey, not a destination. And on that journey, we are still travelling, still discovering, still reaching toward fuller comprehension of what Andromeda truly is and what its size truly means. When the paradigm shift occurred, When astronomers fully grasped that galaxies were embedded in vast dark matter halos, and that size meant something far more complex than they had imagined, the immediate consequences rippled outward through the entire field of astronomy. What had been settled, questions, suddenly became open again. What had been clear classifications became fuzzy. And most importantly, what astronomers thought they knew about cosmic structure had to be rebuilt from the ground up. The first ripple was methodological. If dark matter dominated galactic mass, then measuring galaxies required new approaches. Traditional techniques based on counting stars and adding up their light gave values that were off by a factor of 10 or more. Astronomers needed methods that could detect invisible matter, that could weigh the full structure rather than just the visible parts. Gravitational measurements became essential. By studying how satellite galaxies orbited, how rotation curves behaved at large distances, how light from background objects was bent by gravitational lensing, astronomers could infer the total mass, seen and unseen. These techniques were not new, but they became central rather than supplementary. Every major study of a galaxy now included gravitational measurements alongside photometric ones. For Andromeda specifically, this meant a flurry of new observations. Radio telescopes mapped the hydrogen gas far beyond the optical disk, tracing the galaxy's structure where stars were too sparse to see. Satellites like M32 and M110 were studied more carefully. Their orbits measured with precision to determine how much mass they were orbiting through. Deep optical surveys searched for faint stars in the halo, pushing the limits of detection to find where the visible galaxy truly ended. Each new measurement adjusted the picture. Early estimates of Andromeda's dark matter halo suggested it extended 200,000 light-years beyond the visible disk. Later observations pushed that number higher, perhaps 300,000 light-years, perhaps 500,000, perhaps even farther, until the halo began to overlap with the Milky Way's own dark matter, the two galaxies already touching in their invisible components, even though their visible disks remained millions of light-years apart. This realization that Andromeda and the Milky Way might already be interacting through their dark matter halos was one of the immediate ripples. It meant the collision was not a future event but an ongoing process, already begun in the outer reaches where dark matter dwells. The visible merger would come later, in 4 billion years, but gravitationally the two galaxies were already bound, already influencing each other, already beginning their slow dance toward union. Another consequence was the need to recalibrate distance measurements. The Cepheid variable method remained valid for measuring how far away Andromeda was, but understanding its true size required combining distance with measurements of angular extent, and those measurements became more complicated when trying to include the dark matter halo, which had no sharp edge, no clear boundary where you could say here the galaxy ends. Different research groups adopted different conventions. Some defined the galaxy's size as the radius within which a certain percentage of the mass was enclosed, say 95%. Others used the point where the rotation curve flattened completely. Still others chose the distance where the density of stars or dark matter dropped below some threshold. Each definition was valid for its purpose, but it meant that published sizes for Andromeda varied, depending on who was doing the measuring and what they were trying to capture. This diversity of definitions rippled into public communication. When astronomers said Andromeda was 220,000 light-years across, they usually meant the visible disk. But when they said it was much larger, including dark matter, the numbers varied. Was it 400,000 light-years? 600,000? A million? The answer depended on methodology and definition, and that complexity was hard to convey to non-specialists who wanted a single, clear number. The immediate consequence was a certain loss of precision in public discussions. Before, you could say, Andromeda is this big, and everyone understood what you meant. After, you had to qualify. The visible part is this big. The dark matter halo extends this far. The gravitational influence reaches this far. Each qualifier was necessary for accuracy, but it made communication more difficult. Within the astronomical community, the ripple affected how research was funded and organized. If understanding galaxies required measuring dark matter, then instruments capable of doing so became priorities. radio telescopes that could map hydrogen gas, space-based observatories free from atmospheric interference, computer clusters capable of running complex simulations that included dark matter dynamics. Funding agencies shifted resources toward these capabilities, recognizing that the old ways of studying galaxies were no longer sufficient. Collaborations formed around shared goals. Studying Andromeda's dark matter halo required data from them, multiple wavelengths, multiple instruments, multiple research groups. No single observatory could capture the full picture. Teams from different institutions pooled their observations, compared their measurements, worked together to build a comprehensive model. This collaborative approach became standard, a recognition that understanding something as complex as a galaxy required diverse perspectives and techniques. The paradigm shift also rippled into related fields. Cosmologists studying the early universe realized that understanding how galaxies formed required understanding dark matter's role from the beginning. Particle physicists working on theories of what dark matter might be found renewed interest from astronomers who could provide observational constraints. If dark matter made up 85% of the mass in a galaxy like Andromeda, then understanding its properties was not just an astronomical question, but a fundamental physics question. Another immediate consequence was the recognition that Andromeda's satellites were not just small companions, but valuable probes of the dark matter halo. Each satellite orbited within the halo, its motion shaped by dark matter's gravity. By studying many satellites, each at different distances, astronomers could map how dark matter was distributed, whether it was concentrated near the center or spread more evenly, whether the halo was spherical or elongated. This led to intensive surveys searching for new satellites. The more satellites found, the more data points available for constraining the dark matter distribution. Over the past 2 decades, dozens of new faint dwarf galaxies have been discovered orbiting Andromeda, each adding to the picture. These discoveries were a direct consequence of recognizing that satellites mattered not just as objects in themselves, but as tools for probing the invisible halo. The ripple extended even to how galaxies were simulated in computers. Before, simulations focused on stars and gas, treating gravity as straightforward. After dark matter had to be included from the start, its distribution and dynamics modelled explicitly. The simulations became more complex, requiring more computing power, but they also became more realistic, matching observations more closely. For Andromeda, simulations that included dark matter could reproduce features that purely stellar models could not. The flat rotation curve, the stability of the outer disk, the orbits of satellites. All made sense when dark matter was present. The simulations also predicted features that were then searched for and found, like the extended hydrogen gas disk and the tidal streams from consumed satellites. One particularly striking consequence was the realization that Andromeda had likely consumed dozens, perhaps hundreds, of smaller galaxies over its lifetime. Each time it absorbed a satellite, it gained not just stars but dark matter, adding to its halo. The streams of stars visible in deep images were just the traceable remnants. The dark matter from those galaxies had merged seamlessly into Andromeda's halo, invisible but present, contributing to the total mass. This turned Andromeda's size into a historical record. Its current extent reflected its entire past, every merger, every accretion event. The galaxy was not born large, but had grown to its current size through billions of years of accumulation. Understanding its size meant understanding its history, and understanding its history required tracing all the interactions that had shaped it. The immediate ripple also affected how other galaxies were studied. If Andromeda, one of the closest and best-studied galaxies, was dominated by dark matter, then presumably all galaxies were. Every measurement of every galaxy had to be reconsidered. Were published sizes accurate, or did they underestimate by ignoring dark matter? Were mass estimates reliable? The paradigm shift for Andromeda became a paradigm shift for all extragalactic astronomy. As you sink deeper into stillness, let these ripples fade into the background. The consequence of understanding Andromeda more deeply was that understanding itself became more complex. The immediate effect was not clarity but complication, not simplification but nuance. And yet, this was progress. The universe was revealing itself more honestly, and astronomers were learning to see what had been invisible. The ripples spread outward, touching every corner of the field, changing how galaxies were measured, how they were understood, how their histories were reconstructed. And Andromeda, patient and vast, continued to shine, continued to orbit, continued to drift toward us, unaffected by how much or how little we understood about it. The consequences were human, the ripples were scientific, but the galaxy itself simply was immense and mysterious, waiting for the next generation to look and wonder. The realization that Andromeda was embedded in a vast dark matter halo did not just affect immediate research. Its echoes reverberated through decades, reshaping entire subfields of astronomy, influencing cosmology, and changing humanity's understanding of its place in the universe. The impact was not a single moment, but a long transformation. A gradual adjustment of perspective that continues even now. One of the most profound echoes was in cosmology, the study of the universe's origin and evolution. Before dark matter was understood, cosmological models had difficulty explaining how galaxies formed. In a universe containing only normal matter, structures should have taken much longer to develop. The clumping of matter under gravity was too slow to produce galaxies within the age of the universe. Dark matter solved this problem. Because it did not interact with light or radiation, dark matter could begin clumping earlier, unaffected by the pressure that kept normal matter diffuse. These dark matter clumps created gravitational wells. Normal matter fell into these wells, accumulating at their centers, forming stars and galaxies. Andromeda, like all galaxies, was built on a foundation of dark matter that had been growing since shortly after the Big Bang. This realization transformed cosmology from a field struggling with inconsistencies into one with a coherent framework. The standard model of cosmology, often called lambda CDM, included dark matter as a fundamental component. Lambda represented dark energy, the mysterious force accelerating the universe's expansion. CDM stood for cold dark matter, particles that moved slowly enough to clump effectively. With these components, the model could explain the formation of galaxies, the large-scale structure of the universe, and the patterns seen in the cosmic microwave background. Andromeda's role in this transformation was significant. As one of the closest large galaxies, it provided detailed observations that tested cosmological predictions. The distribution of its satellites, the structure of its halo, the history recorded in its tidal streams, all offered ways to verify or challenge the standard model. When observations matched predictions, confidence in the model grew. When they diverged, it prompted refinements and deeper investigation. Another echo was in the field of galactic dynamics, the study of how galaxies move and evolve. The flat rotation curves observed in Andromeda and other galaxies became a cornerstone of the field. They were not anomalies, but signatures of a universal phenomenon. Every spiral galaxy studied showed similar behavior, evidence that dark matter halos were ubiquitous. This led to the development of sophisticated models of galactic structure. Astronomers learned to decompose a galaxy into components: the central bulge, the exponential disk, the dark matter halo. Each component had its own mass distribution, its own contribution to the gravitational field. By fitting these models to observations, they could infer properties that could not be measured directly, like the concentration of dark matter near the center versus farther out. For Andromeda, these models revealed that its dark matter halo was probably somewhat less concentrated than earlier theories predicted. The core was not as dense as simulations suggested it should be. This discrepancy, known as the core cusp problem, became one of the challenges facing dark matter theory. Was dark matter interacting with itself in ways not accounted for? Were the simulations missing some physics? The question remained open, but Andromeda's structure provided crucial data for addressing it. The impact also echoed through the study of galaxy evolution. Understanding that galaxies grew through mergers, that their sizes increased over cosmic time, changed how astronomers thought about the history of the universe. Looking at distant galaxies, seeing them as they were billions of years ago, astronomers could trace how structures had evolved. Early galaxies were smaller, less massive. Over time, they merged, grew, became the giants we see nearby today. Andromeda, in this context, was not just an object to study but an example of where that evolution could lead. It had grown from smaller progenitors through countless mergers. Its size today was the cumulative result of billions of years of accumulation. By studying its tidal streams, its satellite population, its chemical composition, astronomers could reconstruct its history, piecing together the story of how it became what it is. This historical perspective changed how size was understood. Andromeda is 220,000 light-years across now, but it was smaller in the past and will be larger in the future. Size is not static but dynamic, a point along a timeline that stretches from the galaxy's formation to its eventual merger with the Milky Way and perhaps beyond. The echoes reached into public consciousness as well. The discovery of dark matter, made concrete through observations of past galaxies like Andromeda, became one of the great scientific mysteries of the late 20th and early 21st centuries. What is dark matter? How can we detect it directly? Can it be produced in particle accelerators? These questions captured imaginations, inspiring not just scientists but science fiction writers, educators, and the general public. Andromeda became a symbol in popular culture of the vast unknowns that remain. Here was a galaxy visible to the naked eye, studied for centuries, and yet most of it was invisible, made of something we still do not understand. That combination of familiarity and mystery made it a powerful emblem for the limits and possibilities of human knowledge. Educational programs began using Andromeda as a teaching tool. It was close enough to see, interesting enough to capture attention, and complex enough to illustrate deep concepts. Students could observe it through small telescopes, seeing the bright core and perhaps hints of the spiral arms. Then they could learn about the dark matter halo, the invisible structure surrounding what they had seen. The contrast between the visible and the invisible, between what we can see and what we infer, became a lesson in how science works. The impact on technology was also significant. The need to study dark matter drove the development of new instruments, wide-field survey telescopes that could detect faint stars in galactic halos, radio arrays that could map hydrogen gas with high precision, space-based observatories operating at wavelengths blocked by Earth's atmosphere. Each advance opened new windows on Andromeda and galaxies like it. Gravitational lensing, the bending of light by mass, became a powerful tool for mapping dark matter. When light from distant objects passed near Andromeda, it was deflected by the galaxy's gravity. By measuring the deflection, astronomers could infer the distribution of all matter, visible and dark. This technique, refined over decades, allowed mapping of dark matter structures with increasing precision. Computer simulations also advanced. The need to model galaxies including dark matter pushed the development of more powerful algorithms and faster computers. Simulations that once took months to run could be completed in days. Resolution improved, allowing smaller structures to be resolved, satellite galaxies and tidal streams reproduced in detail. These simulations became essential for interpreting observations, for testing theories, for making predictions. The long-term impact on our understanding of the universe's fate also traces back to dark matter studies. The eventual collision between Andromeda and the Milky Way, predicted with increasing precision, became a template for understanding galaxy mergers throughout cosmic history. Simulations showed that such mergers were common, that they transformed spirals into ellipticals, that they triggered bursts of star formation. The local collision, billions of years in the future, was a local example of a universal process. Another lasting echo was philosophical. The realization that most of the universe is invisible, that we can see only a small fraction of what exists, changed how people thought about reality. It suggested humility. Our senses, even aided by telescopes, show us only part of the picture. Much remains hidden, detectable only through indirect means. This recognition applied not just to dark matter but to the broader question of what might exist beyond our ability to detect. For some, this was unsettling, a reminder of how limited human perception is. For others, it was exciting, a sign that mysteries remain, that the universe still has secrets to reveal. Andromeda embodied both responses. Its visible beauty inspired awe. Its invisible complexity inspired curiosity. Together, they created a richer appreciation for the nature of reality. The echoes continue even now. New observations of Andromeda still refine our understanding. New satellites are discovered. The dark matter distribution is mapped with greater precision. The history of mergers is reconstructed in more detail. Each advance builds on what came before. Each echo connects to earlier discoveries, creating a continuous thread of understanding that stretches back to Al-Sufi, noticing a little cloud and forward to future astronomers who will see things we cannot yet imagine. As you rest now, deeply relaxed, feel the weight of this long impact. Understanding Andromeda changed not just one field but many. Not just science but culture, not just measurements but meaning. The echoes through time show that knowledge is cumulative, that each generation builds on the last, that the question of how big Andromeda is has led to questions about the nature of the universe itself. And Andromeda continues, patient across the ages, its light arriving night after night, its structure evolving on timescales so long that human history is barely a flicker. The impact of understanding it is human, but the galaxy itself transcends that understanding. Existing independently, vast and mysterious, waiting for the next echo, the next discovery, the next moment when someone looks up and wonders. Behind every measurement of Andromeda, behind every calculation of its size and mass, behind every photograph and spectrum and simulation, there are people, individuals who dedicated their lives, or significant portions of them, to understanding a faint blur in the night sky. These are not just names in textbooks or authors on papers, but dreamers who looked up and wondered, who refused to accept mystery as an endpoint, who pushed against the limits of knowledge. Think of Abd al-Rahman al-Sufi, working in 10th century Persia, compiling his book of fixed stars. He had no telescope, no camera, no computer, just his eyes, the dark skies above him, and a determination to record what he saw. When he described the little cloud in Andromeda, he was doing more than cataloguing. He was preserving a question for future generations, ensuring that others would know to look, would know that something unusual dwelt in that constellation. What drove him to this work? It could not have been fame, for his book would not reach European audiences for centuries. It could not have been wealth, for astronomical observations brought little material reward. It must have been something deeper. Curiosity, perhaps, or wonder, or the satisfaction of bringing order to the chaos of the night sky, of finding patterns, of knowing that he understood something about the heavens that others did not. Move forward to Simon Marius, observing through his telescope in 1612, trying to make sense of what he saw. The Andromeda Nebula did not resolve into stars as he might have hoped. Instead, it remained stubbornly fuzzy, like a candle flame through horn. Another astronomer might have moved on to clearer targets, to objects that yielded more obvious results. But Marius described what he saw, carefully and accurately, adding his observation to the slow accumulation of knowledge. Consider William Herschel, the musician turned astronomer, who built his own telescopes and systematically swept the sky. He discovered Uranus, mapped double stars, catalogued thousands of nebulae. His sister Caroline worked beside him, recording observations, performing calculations, making discoveries of her own. Together, they transformed astronomy from a gentleman's hobby into a systematic science. When Herschel observed Andromeda, he noted its nebulous character, its resistance to resolution into individual stars. He speculated that perhaps a more powerful telescope might reveal its true nature. He was right, though it would take more than a century and telescopes far beyond what he could build. His contribution was not the answer, but the careful documentation of the question, the recognition that Andromeda was something worth understanding. Then there is Henrietta Swan, Leavitt, who discovered the period luminosity relation of Cepheid variables while working at Harvard College Observatory in the early 1900s. She was one of many women employed as computers, human calculators who measured photographic plates, recorded data, performed the tedious work that male astronomers often considered beneath them. She was paid little, given less credit than she deserved, yet her discovery became the foundation for measuring cosmic distances. Without Leavitt's work, Edwin Hubble could not have measured Andromeda's distance. Her relationship between a Cepheid's period and brightness was the key that unlocked the scale of the universe. And yet for decades, her contribution was barely acknowledged. She dreamed through her work, finding patterns in what seemed like repetitive tedium, recognizing significance where others saw only data. Edwin Hubble himself was a dreamer of a different sort. Ambitious, confident, eager for recognition, he pursued the biggest questions with the best tools available. When he identified Cepheids in Andromeda and calculated their distance, he knew he was doing something momentous. The discovery that Andromeda was a separate galaxy changed everything, and Hubble was not shy about claiming credit. But even Hubble built on the work of others. The Hooker telescope he used had been constructed through the efforts of engineers and benefactors. The photographic plates he exposed were manufactured by companies perfecting their craft. The mathematical framework he used came from physicists and astronomers who had worked out the laws of light and gravity. He was the culmination of a long chain of effort, the person who happened to be in the right place at the right time with the right tools, and he knew it. Despite his ambition, Hubble understood that science was cumulative, that his achievement rested on foundations laid by others. In his writings, he acknowledged predecessors, cited their work, recognized that the question of Andromeda's nature had been asked long before he answered it. Consider also Vera Rubin, who in the 1970s studied rotation curves of galaxies and found the evidence for dark matter. She was not looking for dark matter specifically. She was trying to understand how galaxies rotated, measuring the velocities of stars and gas at different distances from galactic centers. The flat rotation curves were unexpected, puzzling, revolutionary. Rubin faced skepticism, as many scientists do when presenting results that challenge accepted understanding. Some colleagues questioned her measurements, suggested systematic errors, proposed alternative explanations, but she persisted, refining her techniques, gathering more data, demonstrating that the effect was real. Her work, along with that of Kent Ford and others, established dark matter as a necessary component of galactic structure. Rubin's story reminds us that scientific progress often comes through persistence as much as brilliance. She was a dreamer who refused to dismiss anomalous data, who believed that careful observation could reveal truths even when those truths were uncomfortable or unexpected. Think of the countless graduate students and postdoctoral researchers who have spent nights at telescopes observing Andromeda, who have processed data, written papers, contributed pieces to the larger puzzle. Most of their names are not famous, will never be widely known. But each added something: a measurement of a satellite galaxy, a map of a tidal stream, a spectrum of a star cluster. The understanding of Andromeda's size is built from thousands of such contributions, each small in itself but essential to the whole. There are also the engineers and technicians who built the telescopes, who maintained the instruments, who ensured that observations could be made night after night. Without them, astronomers would have nothing to observe with. Their dreams were perhaps less about the cosmos and more about precision, craftsmanship, solving technical problems. Their work made the astronomical dreams possible, and there are the theorists, sitting at desks or in front of computers, running simulations, solving equations, building models. They dream in mathematics, in code, in abstract structures. Their work connects observations to physical laws, explains why galaxies behave as they do, predicts what observations should reveal. When simulations of galaxy formation, including dark matter, successfully reproduced the properties of real galaxies like Andromeda, it was a triumph of theoretical dreaming. Consider the people working today, right now, still studying Andromeda. Some are using the Hubble Space Telescope to map individual stars in its halo. Others are measuring the motions of its satellite galaxies to constrain the dark matter distribution. Still others are preparing for future observations with the James Webb Space Telescope, planning how to use its infrared capabilities to probe Andromeda's structure in new ways. These modern dreamers stand on the shoulders of all who came before, They have better tools, more data, more computing power. But they share the same fundamental curiosity, the same desire to understand, the same willingness to spend years pursuing answers to questions that might not yield to easy solutions. There is also a personal element to consider. Many astronomers describe a moment when they first truly saw Andromeda, not just as data, but as a real place. For some, it came when looking through a telescope and seeing the spiral structure emerge. For others, it came when working with data and suddenly realizing that each point of light represented an actual star, that the galaxy was not an abstraction, but a physical system of unimaginable scale. These moments of recognition, of connection, fueled the pursuit. They reminded researchers why they were doing this work, why it mattered, why spending cold nights at telescopes or long hours at the computers was worthwhile. The dreamers dreamed not just of answers, but of understanding, of grasping something true about the universe. And the dreams were not only individual, but collective. The astronomical community, for all its competition and occasional conflicts, functioned as a network of shared dreaming. Discoveries were published, shared, built upon. When one group measured Andromeda's distance more precisely, others used that measurement in their own work. When someone found a new satellite galaxy, everyone's understanding of the system improved. The dream of comprehending Andromeda was distributed across hundreds of people, each contributing their piece. There is beauty in this human element, in recognizing that knowledge is not abstract but emerges from specific people making specific efforts. Andromeda's size is known because humans cared enough to measure it, to refine those measurements, to argue about them, to push for greater precision. The galaxy itself was different to these efforts, but the people were not. They invested their lives, their careers, their midnight hours in understanding it. As you breathe softly now, deeply relaxed, think of these dreamers. From Al-Sufi with his naked eyes, to modern astronomers with space telescopes, they form a continuous line. Each looked at the same galaxy, saw it through different tools, understood it in different frameworks, but all shared the impulse to know, to measure, to comprehend. You are part of this lineage too, in a way. When you look up and see Andromeda, when you wonder about its size, you join the chain of curiosity that stretches back across centuries. You may not have a telescope or the mathematics, but you have the wonder. And wonder is where dreaming begins. The human element matters because it reminds us that science is not cold or impersonal, it is deeply human. Driven by the same curiosity that makes us look up at stars, the same desire to understand that makes children ask, why? Andromeda's immensity is a fact, but our knowledge of that immensity is a human achievement, the result of countless dreamers refusing to accept ignorance, pushing toward understanding, building knowledge grain by grain across generations. For every discovery about Andromeda's true nature and size, there were skeptics. For every measurement that pushed understanding forward, there were those who questioned the methods, doubted the results, proposed alternative explanations. This opposition was not obstruction, but an essential part of how science works, how truth is tested and refined. The battle for understanding Andromeda was not won easily, but through argument, evidence, and the slow accumulation of proof that convinced even the doubters. When Edwin Hubble first claimed that Andromeda was a separate galaxy millions of light-years away, not everyone accepted it immediately. Harlow Shapley, one of the most respected astronomers of the time, had argued the opposite position. He believed the Milky Way was the entire universe, that spiral nebulae like Andromeda were part of our galaxy, not separate systems. Shapley had good reasons for his view, based on measurements and interpretations that seemed solid at the time. The Great Debate of 1920, held before Hubble's definitive measurements, pitted Shapley against Heber Curtis, who argued that spiral nebulae were island universes. Both presented evidence, both made compelling arguments, neither convinced the other. The debate ended without resolution, waiting for better data to settle the question. When Hubble's measurements came, showing that Cepheid variables in Andromeda were far too distant to be part of the Milky Way, Shapley faced a choice. He could reject the evidence, could find reasons to doubt, could dig in and defend his position. Instead, After careful consideration, he accepted that he had been wrong. This is science at its best, when opposition gives way not to stubbornness but to honest evaluation of evidence. But not all opposition dissolved so cleanly. Some astronomers questioned the calibration of Cepheid variables. Perhaps the relationship between period and luminosity was not as universal as assumed. Perhaps there were different types of Cepheids with different properties. Perhaps environmental effects changed how they behaved. Each objection had to be addressed with more observations, more careful analysis, more data. The debate over Andromeda's distance continued for decades after Hubble's initial measurement. Different astronomers using different methods arrived at different values. Some said 2 million light-years. Others said 2.5 million. The uncertainty mattered because it affected every other calculation, every estimate of size and mass and luminosity. Resolving this required painstaking work. More Cepheids had to be identified and measured in Andromeda. The period-luminosity relation had to be calibrated more precisely using Cepheids in other galaxies where distances could be determined through independent methods. Statistical techniques had to be refined to account for uncertainties. Gradually, the measurements converged, the opposition quieted, and a consensus emerged. When dark matter was proposed to explain the flat rotation curves in galaxies, the opposition was fierce. The idea that most of the universe was made of invisible, unknown matter seemed extravagant, almost absurd. Many astronomers and physicists resisted. Perhaps the measurements were wrong. Perhaps there were systematic errors in how rotation curves were measured. Perhaps the laws of gravity needed modification at galactic scales, rather than invoking mysterious dark matter. This last alternative, known as modified Newtonian dynamics, or MOND, gained some supporters. It proposed that gravity behaved differently at very low accelerations, like those experienced by stars in the outer reaches of galaxies. Under MOND, the flat rotation curves could be explained without dark matter. For a time, this alternative seemed viable, a simpler explanation that did not require inventing new forms of matter. But as evidence accumulated, MOND struggled. It could explain rotation curves, yes, but it had difficulty with other observations. Gravitational lensing, the bending of light by mass, showed more mass than visible stars could account for, consistent with dark matter but hard to explain with modified gravity. The cosmic microwave background, the patterns of temperature fluctuations from the early universe, required dark matter to match observations. Galaxy cluster dynamics pointed to the same conclusion. For Andromeda specifically, multiple independent measurements of its mass, from rotation curves, from satellite orbits, from gravitational effects on nearby objects, all converged on values consistent with a massive dark matter halo. The opposition had to contend with this weight of evidence. Some remained unconvinced, continuing to explore alternatives, but the mainstream of astronomy accepted dark matter as the best explanation for what was observed. The battle over size definitions also created opposition of a different sort. When some astronomers claimed Andromeda was 400,000 or 600,000 light-years across, including the dark matter halo, others objected. That is not a meaningful definition of size, they argued. The halo has no sharp edge. It fades gradually into intergalactic space. Where do you draw the boundary? Different choices give wildly different answers, making comparison between galaxies difficult. This opposition led to efforts to standardize definitions. Perhaps size should be measured as the radius containing 90% of the luminosity, or the radius where surface brightness drops below some threshold, or the virial radius, where the galaxy's gravity no longer dominates over the expansion of the universe. Each definition had advantages and disadvantages, supporters and critics. The battle was not about who was right in some absolute sense, but about what conventions would be most useful for the field. It was resolved not by proving one side correct, but by establishing clear definitions that researchers could apply consistently, allowing meaningful comparisons even when different definitions gave different numbers. There was also opposition to the idea that Andromeda and the Milky Way would collide. When astronomers first predicted the merger based on Andromeda's motion toward us, some questioned whether the proper motions had been measured accurately. Was Andromeda really headed directly for us, or was it passing by at an angle that would miss? The difference mattered. A direct collision would be dramatic. A near miss might cause tidal disruptions, but not a full merger. Measuring the proper motion of something 2.5 million light-years away is extraordinarily difficult. It requires detecting tiny shifts in position over years or decades, shifts measured in fractions of an arc-second. Early measurements had large uncertainties. Some supported a direct collision, others suggested Andromeda might pass to the side. Only in the 21st century, with data from the Hubble Space Telescope measuring the sideways motion of Andromeda with sufficient precision, was the question settled. The galaxies were indeed on a collision course. The opposition had been reasonable, demanding solid evidence before accepting such a dramatic claim. When that evidence arrived, the opposition faded. Another form of opposition came from those who argued that Andromeda was not particularly special, that focusing so much attention on it was parochial, driven by its proximity rather than its intrinsic importance. Why not study more distant galaxies? They asked. Why not focus on galaxy clusters, or on the large-scale structure of the universe? Andromeda might be nearby, but did that make it representative? This opposition pushed the field in to productive directions. Astronomers did study other galaxies, did expand their surveys to include more distant and diverse systems, but they also recognized that Andromeda's proximity was precisely what made it valuable. It could be studied in detail impossible for more distant galaxies. Individual stars could be resolved, faint structures could be detected. Its properties could be measured with precision that served as benchmarks for understanding galaxies generally. The opposition here was not about whether Andromeda was worth studying, but about balance, about ensuring that the field did not become too focused on one object at the expense of broader understanding. This tension between depth and breadth, between detailed study of nearby systems and surveys of many distant ones, remains productive, driving both approaches forward. Throughout all these battles, the underlying principle was that science advances through skepticism as much as through discovery. Opposition forces researchers to check their work, to gather more evidence, to consider alternatives. When opposition is answered with solid data and sound reasoning, understanding deepens. When opposition reveals genuine problems, the field corrects course. For Andromeda, the cumulative effect of these battles was a more robust, more thoroughly tested understanding. Every measurement that withstood skepticism became more reliable. Every claim that survived opposition became stronger. The size of the galaxy, the evidence for dark matter, the prediction of collision, all were refined through the process of being challenged and defended. As you relax now, sinking deeper into rest, consider that truth is not always obvious, not always immediately accepted. The path to understanding Andromeda was not straight but winding, marked by debates and disagreements, by opposition that sometimes seemed obstructive, but ultimately served to strengthen the foundation of knowledge. The galaxy itself was unchanged by these human arguments, but our knowledge of it was forged in the fire of skepticism, tested and refined until it could stand firm. The opposition matters because it shows that science is not dogmatic but self-correcting, not about authority but about evidence, not about winning arguments but about approaching truth as closely as human effort allows. And in the case of Andromeda, the result of all these battles is a picture that, while still incomplete, is solid enough to build on, detailed enough to inspire, and true enough to trust. There comes a moment in understanding when something shifts, not just intellectually but experientially, when you move from knowing facts to feeling their implications. For many who study Andromeda, and for those who simply look up and see it with informed eyes, there is an awakening, a realization that changes how the galaxy appears, how the night sky feels, how our place in the universe is perceived. The awakening often begins with scale. You can know, intellectually, that Andromeda contains 1 trillion stars, that it stretches 220,000 light-years across, that its light takes 2.5 million years to reach us. You can hold these numbers in your mind, repeat them, even calculate with them. But understanding them, feeling what they mean, is different. It might happen when you are standing outside on a clear night, looking up at that faint blur. and suddenly the scale clicks. That smudge is not small, it is enormous, larger than anything you have ever seen or touched or travelled across. Each point of light within it, too faint for your eyes to separate, is a sun. Some of those suns are larger than ours, some smaller, but each burns with its own nuclear fire, each exists across its own gulf of space. And more than that, around some of those suns orbit planets, rocky worlds, gas giants, perhaps moons with subsurface oceans, perhaps atmospheres that could shelter life. The number of possible worlds in Andromeda is almost certainly in the trillions. Most will be barren, hostile, empty, but even a tiny fraction that are not represents more opportunity for complexity, for chemistry, for biology than we can easily imagine. This realization that Andromeda is not just large but full, not just distant but real, inhabited by actual physical systems operating under the same laws as our solar system, can be awakening. You are not looking at an abstraction but at a place, a region of space where things happen, where stars are born and die, where galaxies once merged, where perhaps at this very moment someone or something looks back toward the Milky Way and wonders. The awakening also comes from recognizing the temporal dimension. The light you see left Andromeda 2.5 million years ago. You are seeing the past, a fixed moment in the galaxy's history. The Andromeda of now, the one that exists at this instant, is invisible to you, will remain invisible for another 2.5 million years. This means that the galaxy you see is younger than the one that exists. Stars that have since been born are invisible to you. Stars that have since died still shine in your view. The galaxy is both there and not there, both real and a ghost. This temporal displacement, once truly felt, changes how you perceive the act of looking. You are not observing the present, but reading history, seeing events that unfolded before humanity existed. Another aspect of the awakening is the recognition of motion. Andromeda is not static in space, but moving toward us at over 100 kilometers per second. Every second, the distance between our galaxies decreases by more than 100 kilometers. That sounds fast, and it is by human standards, but across the 2.5 million light-year gulf, it is glacially slow. Still, the motion is real and relentless. In 4 billion years, give or take, the galaxies will collide. This is not speculation but prediction based on solid measurements. The merger is inevitable. Already written into the motion of the galaxies, into the gravity that binds them. You are seeing not just a galaxy but a future partner, a system that will one day blend with our own. When this realization settles, the night sky transforms. You are not just looking at stars scattered randomly across the heavens. You are looking at systems in motion, at galaxies dancing under gravity's influence, at a cosmos that is dynamic, evolving, heading toward futures we can predict even if we will not be here to witness them. The faint blur becomes a messenger from the future as well as the past, a sign of what is to come. The awakening also involves recognizing our insignificance and our significance simultaneously. Insignificance because compared to Andromeda, compared to the trillion stars it contains, compared to the scales of time and space involved, we are vanishingly small. Our planet is a speck. Our lives are flickers. The entirety of human history is a thin line drawn across a canvas billions of years old. And yet, significance because we are the ones observing, measuring, understanding. As far as we know, we are the only beings in this region of space capable of comprehending what Andromeda is. We have built the tools to see across millions of light years. We have developed the mathematics to calculate its mass, predict its motion, trace its history. The galaxy is immense, and we are small, but we bridge that immensity with thought, with science, with curiosity. This dual awareness, holding both smallness and capability at once, is part of the awakening. You are not erased by the scale but placed within it, given a position that is both humble and remarkable. To stand beneath Andromeda and know what you are seeing is to participate in something rare, perhaps unique in the cosmos. Consciousness, observing itself, the universe becoming aware of its own structure through human minds. The awakening can also be emotional. Some people report feeling a kind of calm when contemplating Andromeda, a settling of daily anxieties against the backdrop of cosmic scale. If galaxies operate on timescales of billions of years, if the universe is so vast, then perhaps the stresses of human life are not as overwhelming as they feel. This is not to diminish those stresses, which are real and important on human scales, but placing them in context, seeing them as part of a much larger picture, can bring perspective, a kind of peace. Others feel excitement, a thrill at the sheer improbability of being able to see another galaxy. The photons reaching your eyes travelled for millions of years to get there. The stars that emitted them existed long before you, will exist long after you. And yet, here you are, able to catch that ancient light, to interpret it, to understand its source. The connection feels almost impossible, a bridge across space and time that should not exist but does. There is also the awakening that comes from recognizing the commonality of matter. The atoms in your body were forged in stars, not in Andromeda's stars specifically, but in stars like them, in earlier generations that lived and died, scattering their enriched material into space. You are made of stardust, literally, and so is everything around you. The carbon in your cells, the iron in your blood, the calcium in your bones, all were created in stellar cores and supernova explosions. Andromeda's stars are doing the same thing now. They are fusing hydrogen into helium, helium into heavier elements, creating the building blocks of planets and life. When some of those stars die, they will scatter those elements into space, where they might one day be incorporated into new stars, new planets, perhaps even new beings. The cycle continues, universal, connecting all matter across the cosmos. This recognition can create a feeling of kinship with the galaxy. You are not separate from it, but part of the same process, made of the same stuff, operating under the same laws. The distance is vast, yes, but the connection is real. You are both products of the same universe, expressions of the same fundamental physics. The awakening does not happen all at once. It comes in layers, over time, through repeated exposure to the ideas and to the sight itself. The first time you see Andromeda with your eyes, you might notice only a faint blur. The second time, knowing what it is, you see more, feel more. Each subsequent encounter deepens understanding, adds nuance, builds toward a fuller awareness, and the awakening is personal. What strikes one person as profound might leave another unmoved. Some find meaning in the scale, others in the motion, others in the history. There is no single correct way to awaken to Andromeda's reality. The important thing is the shift from abstraction to presence, from numbers to felt experience, from knowing about the galaxy to encountering it. As you breathe deeply now, completely at ease, let this awakening touch you gently. You have travelled through the story of Andromeda, from ancient observations to modern measurements, from debates about size to realizations about dark matter. You have met the dreamers and the skeptics, traced the ripples of discovery, felt the weight of immensity. Now, in this quiet moment, let all of that settle into a simple awareness. Andromeda is there, you know what it is, and knowing changes how you see it, how you feel beneath the stars, how you understand your place in the vastness. The awakening is not dramatic but quiet, a gentle shift in perspective that makes the ordinary sky extraordinary, the faint blur a window into immensity. And once awakened, you carry that awareness with you, a gift from the cosmos, a reminder that you are part of something vast and wondrous and real. After all the measurements, after all the theories and debates, after tracing the history and meeting the dreamers, after awakening to the scale and significance, we arrive at the deepest truth about Andromeda. It is not a truth about size in kilometers or light years, not a count of stars or a calculation of mass. It is something more fundamental, something that ties together everything we have explored and reveals what the question of how big Andromeda is really means. The deepest truth is this. Andromeda shows us that size is not about boundaries but about relationships. The galaxy is not an isolated object with a fixed perimeter. It is a node in a network, connected to other galaxies through gravity, to the cosmic web through its position in space, to us through shared history and eventual destiny. Its size is meaningful only in relation to these connections. Consider the dark matter halo. It extends far beyond the visible disk, perhaps 1,000,000 light-years from the centre, but even that is not the full extent of Andromeda's influence. Its gravity affects objects farther still. Satellite galaxies that orbit at greater distances, streams of gas that connect to the intergalactic medium, perturbations in the cosmic web that reach across tens of millions of light-years. Where does Andromeda end and the rest of the universe begin? There is no sharp line. The galaxy fades gradually into its surroundings, its density dropping but never quite reaching zero, its gravitational field weakening but extending theoretically to infinity. Every particle in the universe feels Andromeda's gravity, however faintly. In that sense, the galaxy is as large as the universe itself, though its effect becomes negligible at great distances. This reveals that the question of size is ultimately a question of what we choose to measure and why. If we are asking about the visible stellar disk, the answer is 220,000 light-years. If we are asking about the dark matter halo, the answer might be 500,000 or 1,000,000 light-years. If we are asking about the region where Andromeda's gravity dominates, the answer changes again. Each is correct for its purpose. None captures the full reality. The deepest truth also involves time. Andromeda's size is not constant but evolving. 4 billion years ago, it was smaller, having accreted less mass from its environment. 4 billion years from now, it will be larger, merged with the Milky Way into a new galaxy, sometimes called Milkomeda or Milkdromeda. Size is a snapshot of a process, a temporary state in an ongoing evolution. This temporal dimension means that asking how big Andromeda is requires specifying when. The galaxy you see tonight, as it was 2.5 million years ago, had a certain size. The galaxy as it exists right now, invisible to you, has grown slightly larger through continued accretion. The galaxy as it will exist in the future will be larger still. Size is not static but dynamic, a moving target on a cosmic timeline. Another layer of the deepest truth is that Andromeda redefines what we mean by individuality. We speak of the Andromeda galaxy as though it were a single entity, but it is more accurately a system of systems. The main spiral structure, yes, but also dozens of satellite galaxies, streams of stars from past mergers, clouds of gas extending into the halo, a supermassive black hole at the centre, and the all-encompassing dark matter halo. Is Andromeda one galaxy, or many? The satellites orbit within its gravitational well, their fates tied to its future, yet they have their own structures, their own histories. The tidal streams were once separate galaxies, now torn apart and incorporated. At what point does a consumed galaxy stop being itself and become part of Andromeda? The boundary is fuzzy. The distinction, artificial in some ways. This challenges our intuitive sense that objects have clear identities. Andromeda is both singular and multiple, both itself and a collection of merged components. Its size includes not just its own original matter, but everything it has gathered, and the boundary between self and other is blurred by billions of years of interaction. The revelation extends to our own relationship with Andromeda. We are not outside observers looking at something separate. We are part of the same local group, bound by the same gravity, heading toward the same merger. The Milky Way and Andromeda are not independent, but interconnected, partners in a slow dance that will ultimately unite them. In a very real sense, we already belong to the same system, though the merger is still billions of years away. This means that studying Andromeda is studying part of our own future. The galaxy you see in the sky will one day surround us, its stars mingling with ours, its black hole spiraling toward ours, its structure blending into a new configuration. Understanding Andromeda's size is understanding the size of what we will become, the scale of the system that will contain our solar system. If it still exists, then the deepest truth also touches on the limits of knowledge. For all we have learned about Andromeda, mysteries remain. The nature of dark matter is still unknown. The exact history of mergers is partially reconstructed but incomplete. The internal dynamics, the detailed structure of the spiral arms, the distribution of planets around its stars, all contain uncertainties. We know much, but much more remains hidden, and this is appropriate. The deepest truths should retain some mystery. To know everything would be to lose the sense of wonder, the drive to keep looking, the recognition that the universe always holds more than we have yet grasped. Andromeda is knowable in part, but never fully, never completely. There will always be another layer, another detail, another question. Perhaps the most profound aspect of the deepest truth is that Andromeda exists independently of our understanding. The galaxy was there long before humans evolved, will be there long after we are gone. It does not care whether we measure it correctly, does not change based on our theories, does not need us to observe it. Its size is what it is, regardless of whether anyone knows or asks. And yet, our understanding matters. Not to the galaxy, but to us. In measuring Andromeda, in asking how big it is, in pursuing that question through centuries of effort, we have done something remarkable. We have reached across an unimaginable gulf and touched something real with our minds. We have taken photons that travelled for millions of years and decoded their message. We have used mathematics and physics to understand structure we cannot visit, cannot touch, can barely see. This act of understanding is itself a kind of size, not physical size but intellectual reach, the ability of consciousness to extend beyond its immediate surroundings and comprehend the cosmos. Andromeda is 220,000 light-years across. Our understanding spans that distance and more, encompassing not just the galaxy's extent but its history, its composition, its future. Deepest truth, then, is that Andromeda is as big as the web of relationships that connect it to everything else, as big as the time it has existed and will exist, as big as the questions it raises and the understanding it inspires. Its size is not a single number but a tapestry of measurements, meanings, connections. To ask how big it is receives not one answer but many, all true, all partial, all pointing toward a reality that exceeds any simple description. As you rest now, profoundly relaxed, let this revelation settle without effort. You do not need to hold all the details, do not need to remember every measurement. What remains is the essential recognition that size is complex, that Andromeda is vast in ways both measurable and immeasurable, that the act of asking how big it is opens doors to questions about relationships, time, identity, and the limits of knowledge itself. The deepest truth is not an ending, but an invitation to keep looking, keep wondering, keep recognizing that the universe is always larger, stranger, more intricate than we imagine, and Andromeda, patient across the void, continues to offer itself as a subject of contemplation, a reminder of immensity, a window into the nature of reality itself. We have journeyed far through the story of Andromeda. From ancient observers noticing a faint blur to modern astronomers mapping dark matter halos, from debates about whether it was even a separate galaxy to predictions of its eventual collision with our own, we have explored measurements and mysteries, dreamers and skeptics, awakenings and revelations. Now, as we near the end of this long night's journey, it is time to pause and reflect, to ponder what it all means. What does it mean to know that Andromeda contains 1 trillion stars, not just intellectually, but existentially, humanly, personally? It means that the universe is far more populated with possibility than our everyday experience suggests. Each star is a sun, and around many of those suns orbit planets. Some of those planets might harbour life, simple or complex, fleeting or enduring. The number of opportunities for biology, for chemistry, for complexity is staggering. And this is just one galaxy. The observable universe contains hundreds of billions of galaxies, each with billions or trillions of stars. The scale of possibility expands beyond comprehension. If we are alone in the universe, it would be an almost incomprehensible waste of space. More likely, we are not alone, and Andromeda, like the Milky Way, hosts other forms of consciousness, other observers looking up at their own skies, asking their own questions. What does it mean to see light that has travelled for 2.5 million years? It means that the act of looking is also an act of time travel, a direct connection to the past. The photons entering your eyes carry information from before humanity existed. They are messengers from a time we cannot visit, a record preserved in the speed and persistence of light. This gives astronomy a unique character among sciences. Physicists can manipulate particles, chemists can mix compounds, biologists can observe living systems, but astronomers cannot touch what they study. They can only gather light, ancient light, and decode its message. The remoteness is both limitation and gift. Limitation because direct experimentation is impossible. Gift because it allows us to see history directly, to observe the universe not just as it is, but as it was. What does it mean that most of Andromeda is invisible dark matter? It means that reality is not limited to what we can see, that the universe operates on principles we are still discovering, that humility is appropriate when making claims about what exists. For centuries, humans believed that what could be seen was what existed. Invisible things were dismissed as imaginary or spiritual. Dark matter challenges that assumption. Here is something invisible, undetectable directly, yet undeniably real, proven through its gravitational effects. It suggests that other aspects of reality might also be hidden, not because they do not exist, but because we lack the tools or concepts to detect them. The universe may be far stranger than we currently understand, and Andromeda, in its invisible vastness, reminds us of that strangeness. What does it mean that Andromeda and the Milky Way will merge? It means that nothing is permanent, not even galaxies. The structures we see today are temporary arrangements of matter, destined to change, to blend, to transform. The spiral shape of Andromeda, so beautiful in photographs, will be erased by the merger, replaced by an elliptical galaxy with no arms, no disk, just a smooth distribution of stars. This impermanence applies to everything. Stars are born and die, planets form and are destroyed. Solar systems exist for billions of years but are not eternal. Even the atoms that make up our bodies will eventually scatter, be incorporated into other structures, other systems. Nothing lasts forever except the underlying fabric of the universe itself, and even that may evolve in ways we cannot yet predict. This recognition of impermanence need not be depressing. It can be liberating, a reminder to appreciate what exists now, in this moment, because it will not always be as it is. Andromeda as a spiral galaxy is a temporary configuration, beautiful because it is fleeting. The sky we see tonight will not be the sky of the far future, and that makes it precious. What does it mean that human minds can comprehend a galaxy? It means that consciousness, whatever it is, has a remarkable property. It can hold within itself representations of things vastly larger than itself. Your brain, a few pounds of biological tissue, can contain the concept of a trillion-star galaxy stretching hundreds of thousands of light-years. It can grasp timescales of billions of years, distances measured in units light itself takes eons to traverse. This representational capacity is mysterious in its own right. How does matter organized in a particular way gain the ability to model other matter, to simulate the universe internally, to understand laws and structures that span scales far beyond the individual? Andromeda exists in physical space, but it also exists in the space of human understanding, in the minds of those who study it, who think about it, who look up and recognize what they are seeing. This suggests that size is not just about physical extent, but about cognitive reach. Andromeda is big in kilometers, yes, but it is also big in meaning, in the space it occupies in human thought, in the questions it raises and the understanding it demands. The galaxy's immensity is matched by the immensity of the effort to comprehend it, generations of observers building knowledge piece by piece. What does it mean to stand beneath the sky and know what you are seeing? It means that you are participating in something rare, perhaps unique in the cosmos. As far as we know, humans are the only species in this region of space capable of scientific understanding. We have built the tools, developed the mathematics, pursued the questions that allow us to see beyond immediate experience. This is both privilege and responsibility. Privilege because we get to know, to understand, to experience the wonder of comprehension. Responsibility, because with knowledge comes stewardship, an obligation to preserve what allows understanding to continue, to pass knowledge to future generations, to use our capabilities wisely. Standing beneath Andromeda, you are the universe becoming aware of itself. The atoms in your body, forged in ancient stars, have organized into a form capable of contemplating other stars, other galaxies, other scales of existence. This self-awareness is remarkable, an emergent property of complexity, a gift of evolution and culture and curiosity. What does it mean that mysteries remain? It means that understanding is a journey without end, that each answer opens new questions, that the universe is inexhaustible in its capacity to surprise and challenge us. We know much about Andromeda, but we do not know everything. Dark matter remains mysterious. The detailed history of the galaxy is partially reconstructed but incomplete. The future merger can be predicted in broad outline but not in specific detail. These gaps in knowledge are not failures but invitations. They say there is more to discover, more to understand, more work for future generations. The questions we cannot answer today might be answered tomorrow, or in 100 years, or in 1,000. The pursuit of understanding continues, building on what came before, reaching toward what lies ahead. Reflecting on Andromeda also means reflecting on scale and perspective. The galaxy is immense by human standards, yet it is only one of hundreds of billions. It dominates the local group, yet the local group is a tiny corner of the universe. The observable universe itself may be only a fraction of what exists, and what exists may be embedded in structures or dimensions we cannot yet conceive. This nesting of scales, from human to galactic to cosmic, places us in context. We are small but not insignificant, brief but not meaningless, limited but not helpless. Our size does not determine our value. A thought can be profound regardless of the size of the brain thinking it. A life can matter even if it lasts only decades in a universe billions of years old. As you breathe deeply now, perfectly still, let this reflection wash over you. The meaning of Andromeda is not single but multiple, not fixed but evolving. Not about the galaxy alone, but about what it reveals regarding existence, consciousness, time, scale, and the nature of understanding itself. To ponder its size is to ponder all of this. To sit with questions that have no easy answers, to feel both small and vast, both ignorant and wise, both separate from and connected to the cosmos. The reflection does not lead to certainty but to wonder, not to closure but to openness. Andromeda hangs in the sky, patient and immense, offering itself night after night to those who look up. And in looking, in wondering, in pondering the meaning, we fulfill something essential to being human. We reach beyond ourselves, we connect to something larger. We participate in the universe's long conversation with itself, a conversation that began billions of years ago and will continue long after we are gone. We have travelled far tonight, from the first observations of a little cloud in ancient Persia to the sophisticated measurements of modern astronomy, from debates about whether Andromeda was part of our galaxy to certainty that it is a separate system bound to merge with us, from visible light to dark matter halos extending millions of light years, from simple questions about size to complex reflections on meaning, time, and consciousness. Now, as our journey draws to a close, it is time to return. To come back from the immensity of galaxies to the quietness of this moment, to carry with us what we have learned while leaving behind the weight of too much detail. What remains as Andromeda's legacy? First, there is the legacy of wonder. For thousands of years, humans have looked at Andromeda and wondered what it was. That wonder has not diminished with understanding. If anything, it has deepened. Knowing that the faint blur contains 1 trillion stars, that it spans hundreds of thousands of light years, that it is moving toward us across millions of years, makes it more wondrous, not less. This is one of the gifts of science. It does not destroy mystery but transforms it, revealing complexity and beauty that naked eyes alone could never see. The wonder of the ancient observer seeing a fuzzy patch is matched by the wonder of the modern astronomer, seeing spiral arms resolved into individual stars, seeing the architecture of dark matter, seeing the story of cosmic evolution written in light. The legacy continues through education. Every person who learns about Andromeda, who understands what they are seeing when they look at that faint smudge, carries forward the knowledge accumulated over centuries. The galaxy becomes not just an object in the sky, but a connection to human history, to the long effort to understand the cosmos, to the dreamers who refuse to accept ignorance. Teachers showing students how to find Andromeda, planetariums projecting its image, books and videos explaining its properties. All of these carry the legacy forward. Each new generation inherits the knowledge of the previous ones and builds upon it. The questions change, the tools improve, but the fundamental curiosity, the desire to know, persists. There is also the legacy of humility. Andromeda reminds us that we are not the center of the universe, not the largest structure, not the most important system. We are one planet around one star in one galaxy, among hundreds of billions. This perspective is valuable. It guards against arrogance, against the assumption that human concerns are cosmic concerns, against inflating our significance beyond what is reasonable. At the same time, Andromeda offers a legacy of capability. We are small, yes, but we have reached across 2.5 million light-years with our minds. We have measured what seemed unmeasurable, understood what seemed incomprehensible, predicted futures billions of years away. This is an achievement worth recognizing, a testament to what consciousness can do when it persists, when it questions, when it refuses to stop at easy answers. The legacy extends into the future. Long after we are gone, Andromeda will continue its journey toward the Milky Way. The collision predicted for 4 billion years from now will reshape both galaxies, creating something new from the merger. That future system will be the legacy of both galaxies, a blending of their stars and gas and dark matter into a unified whole. If humanity or its descendants still exist then, they will witness skies unlike any we can see today. The familiar constellations will be disrupted. The Milky Way's band will change as tidal forces reshape the disk. Andromeda will grow from a faint blur to a sprawling presence dominating the heavens. Over millions of years, the two galaxies will pass through each other, fall back together, ultimately merge. Those future observers will see the culmination of a process we can only predict, the realization of the motion we measure today. They will inherit a galaxy built from two, a system that carries the history of both. In that sense, Andromeda's legacy is also our legacy, the two inextricably linked. But we do not need to wait billions of years to experience the legacy. It is here now, every clear night, waiting to be seen. The faint blur in the autumn sky, modest and patient, carries all of this history and future within it. To look at it with informed eyes is to see not just light but time, not just stars but stories, not just a galaxy but a connection across the vastness. The legacy of Andromeda is also practical. The techniques developed to study it, from Cepheid variable measurements to gravitational lensing to spectroscopy, are applied to galaxies throughout the universe. Andromeda was a testing ground, close enough to study in detail, and the lessons learned there have shaped how all galaxies are understood. Every time an astronomer measures the distance to a far galaxy, they use methods refined on Andromeda. Every time someone maps dark matter in a galaxy cluster, they apply principles learned from rotation curves in nearby systems like Andromeda. The legacy is methodological, a foundation of techniques and understanding that supports the entire field of extragalactic astronomy. And now, as we return from this long journey, we come back to where we began, with you lying still, breathing slowly, letting your thoughts drift. The journey through Andromeda's story was a journey through human curiosity, through the history of astronomy, through the nature of size and scale and meaning, but it was also a journey designed to carry you gently towards sleep, to let the immensity become soothing rather than overwhelming. The legacy of this night is the quiet you now feel. The questions have been asked, the story told, the measurements shared. What remains is the simple fact of the galaxy's presence, the knowledge that it is there, and the peace that comes from letting vastness wash over you without needing to hold every detail. When you wake tomorrow, Andromeda will still be there, waiting in the sky, patient as always. You can look for it on clear autumn evenings, let your eyes adjust, find that faint blur, and now, knowing what it is, the blur will mean more. It will be not just light but legacy, not just a galaxy but a connection to centuries of human effort, to the immensity of the cosmos, to the wonder that keeps us looking up. The closing of this story is not an ending but a return to the beginning, to the simple act of noticing a faint cloud and asking what it is. The answer has taken us through immensity and brought us back, enriched by the journey, quieted by the scale, grateful for the capacity to wonder. So, rest now. Let the story settle into your memory like stardust settling into a nebula. Slowly, gently, becoming part of the structure, Andromeda continues its orbit, continues its slow drift toward us, continues to shine across the void. Its trillion stars burn on, indifferent to whether anyone watches, yet somehow more meaningful because we do. The night sky is full of galaxies, but Andromeda is ours, our nearest major neighbour, the one we can see without instruments, the one that will someday merge with us. Its size is both a measurement and a mystery, both a number and a feeling, both a fact and an invitation to wonder. How big is Andromeda really? It is as big as the questions it raises, as big as the knowledge it has inspired, as big as the wonder it creates in those who look up and see. It is 220,000 light-years across, and it is infinite in meaning. It is a trillion stars, and it is one galaxy. It is far away, and it is coming closer. It is ancient light, and it is future destiny. It is there, always there, waiting for you to notice, to wonder, to understand. And having journeyed through its story tonight, you carry that galaxy with you now, not in your eyes alone, but in your mind, in your awareness, in the quiet recognition that you are part of a universe vast beyond imagining, and small enough that a single consciousness can hold it all, can contemplate the immensity, it can rest beneath the stars, knowing what they are, and feeling the peace that knowledge brings. Sleep well beneath Andromeda's light. Dream of galaxies and time, and when you wake, remember that the universe is always there, always vast, always waiting for the next curious mind to look up and ask how big it really is.